Okay. Hello. Good morning from Spain and welcome to everyone to the webinar of Tailing Dam Safety. I'm Carlos Granell, President of the Spanish National Committee of Large Dams. And I am giving you the welcome to this webinar, which has been organized jointly with the Australian National Committee. I want to say that this is the third webinar that SPANCOLD has organized this year. The first one was about the bulletin, the ICOLD bulletin on RCC and CMD dams. The second one that we held before summer here in Spain was one about digitalization, numerical models and BIM. We think in SPANCOLD, and I think that also in the Australian National Committee, that this is today a very good way to do the dissemination of the different techniques related with dams. So we have the intention in the future to continue with this way, okay? First of all, I want to thank the Australian National Committee, ANCOLD, Mr. Angus Swindon. Thank you very much for the co-organization of the webinar. I hope that in the future we can strengthen our relations and do more activities like this one. And I want to also especially thank to all the panelists that are going to speak today about tailing dams. I think that we have a very ambitious program and a very high-level panelists. And finally, I simply want to thank very especially to my friends and colleagues, Manuel Gómez de Membrillera and Francisco Sánchez Caro, who have been the engineers that have organized this in collaboration with the Australian National Committee. And with no more, I gave the floor for Angus Swindon, President of the Australian National Committee of Large Dams. Thank you very much.
Okay, thank you so much, Carlos. And I'll add my welcome to that. I'm really pleased to be able to just spend a few minutes introducing you to ANCOLD and some of what we do at ANCOLD. And I'm really pleased that this collaboration between ANCOLD and SPANCOLD, and it includes some of our very eminent Australian engineers and practitioners, particularly in tailings dam safety. So I'm really pleased that this has happened. And as you say, Carlos, looking forward to some further collaboration down the track. I do have a few slides that I will show. So I will now share my screen. I will try not to take too long, but I thought I'd just give some very high-level outline of what we do, particularly around some of our technical content that we produce that may be of interest to people in SPANCOLD. So if I can get this to advance. Just on ANCOLD, we are a member association of organisations and individuals. We have over 90 members now and over 300 associate members. It's very interesting to note that since the release of our tailings dams guidelines in 2012, the membership of tailings companies and individuals has increased greatly. And I think this is a credit to the people who put a lot of work into producing that guideline, David, Brett, and a range of other people. And now Brett Stevens has taken on responsibility for the review of that guideline. So we really appreciate that work. So I thought I'd just show you a few of our key guidelines that we have produced and that we utilize and how they work together, because this is one of the key deliverables from ANCOLD that we put a lot of effort into. Our guidelines, I think, have become recognized worldwide, and we do get a lot of requests to supply guidelines to international countries. So those three there, consequence categories for dams, dam safety management and risk assessment, are probably our core guidelines around the management of dams through their whole of life cycle. And then there's a range of supporting guidelines that follow that, that we have produced, which I'll show you in a map in a moment. And one of the key ones of those now is the guidelines on tailings dams. I've put together just a slide to show how they work together. It's sort of interesting to see because some of our guideline working groups and under I suppose the oversight of a steering committee that we've only just recently formed are going to look at trying to integrate our guidelines a little bit better. So I know Brett Stevens is spending quite some time with the tailings guideline and also on the dam safety management guideline group to make sure that they are integrated so that the approach to managing tailings is reflected in our management of dams holistically. We have those the key guidelines, including one that is close to being released, I guess, are those four, and the ones that we're about to release are the dam break and consequence assessment, dam safety emergency planning, and retarding basins. So I guess that's the suite of documents that we provide and we make available to the industry, and that is a large part of the work that our volunteer groups undertake. I just showed this one. The Dam Safety Management Guideline outlines all the elements that have been determined to be in a dam safety program. This is one thing that I know Brett Stevens is looking to try and reflect in the dam safety, or sorry, the tailings dams guidelines, so that, as I say, it's more integrated with management of dams across our other portfolios. And this guideline is currently under review. And that one we expect to be released probably in the next 12 to 18 months. And that will be a big step towards a more integrated suite of guidelines. The last thing I'll talk about is risk. So Australia has overtly chosen to go down a risk management path for our major dams. This guideline on risk assessment was re-released in July 2022. And the key element to that is trying to set a limit of tolerability for safety, below which all risks shall be deemed to be as low as reasonably practicable, and above that level, urgent action is taken to reduce the risk profile. Now, the application of this to tailings dams is not something that I have ever worked on because I don't have a background in tailings dams, but I know that our Australian presenters that you're going to be hearing from today are very well versed in the application of risk to tailings dams. So that's all I wanted to say, I suppose. Thank you, Carlos, and I really appreciate the opportunity just to say a few words on behalf of ANCOLD, and I would really like to support you and your committee, and particularly in collaboration with organisations like ANCOLD to try and raise the practice and try and get some broader international collaboration.
Thank you, Angus. I think now that the word is for Francisco Sánchez Caro and Manuel Gómez de Membrillera, who are going to introduce the object of the purpose of the webinar.
Okay, thank you. Paco Sánchez Caro is speaking, chairman of the SPANCOLD Technical Committee on Tailings Dams. I'm going to speak in Spanish, asking Manuel to be kind enough to translate these words. Mis primeras palabras las quería dedicar al catedrático emérito de la Universidad Politécnica de Madrid, don José María Rodríguez Ortiz, recientemente fallecido, y que fue coautor de una de las ponencias que más tarde se presentarán. Tuve el privilegio de trabajar con él en diversas ocasiones y muy especialmente durante la construcción del Metro de Quito en Ecuador. Sirvan estas breves palabras como un sencillo homenaje a su trayectoria profesional y personal, y descanse en paz. Obviamente, lo primero que quisiera es dar la bienvenida a todos nuestros ponentes que participan tanto desde España como desde Australia, agradeciéndoles su participación y reconociendo la elevada calidad técnica de sus trabajos. Los temas técnicos a analizar en la presente webinar están ligados a la seguridad de las presas de estériles mineros. Son presas bastante singulares, ya que son infraestructuras dinámicas en el sentido de que su geometría va evolucionando con el tiempo y además el elemento almacenado obviamente no es agua y no es, por tanto, inocuo. Todo ello unido a que históricamente no se les ha dado la importancia que merecen, ya que en cierta medida son el basurero de las instalaciones mineras en muchos casos, hace que estas presas sean especialmente sensibles a experimentar accidentes graves e incidentes de importancia. Por ello, se considera del máximo interés revisar en esta webinar algunos de los mecanismos de fallos singulares, especialmente el de ecuación por flujo, los procedimientos de mejora del control del comportamiento mediante su correcta auscultación, el manejo adecuado de las aguas de filtración y la revisión de algunos casos históricos que se creen de interés. Las ponencias que aquí se presentarán se realizarán bien en inglés, bien en español, según la preferencia de cada autor. Es difícil coordinar una webinar de este tipo, fundamentalmente por la diferencia de horarios. Por ello, empezaremos con las ponencias que se presentarán desde Australia, cuyo desarrollo será coordinado por Manuel Gómez de Membrillera, y posteriormente daremos paso a las ponencias presentadas desde España. Finalmente tendremos un pequeño coloquio sobre los aspectos técnicos tratados. Espero que todo ello sea del agrado de la totalidad de los participantes en este webinar. Muchas gracias.
Muchas gracias, Paco. Voy a hacer la traducción al inglés. También todas las personas que están conectadas, se puede utilizar el chat o el botón de preguntas y respuestas para cualquier cuestión que se quiera plantear y que, bueno, podemos aprovechar luego para el coloquio. So I will translate into English the introduction done by Paco. And just a reminder to everybody attending today, you have the chat and the Q&A button. So any questions, any subjects, any things you want to bring up, just feel free to use the chat, and we can pick that up for the panel discussion in the end. So in Paco's introduction, he started off really dedicating his first words to the recently deceased emeritus professor from the Technical University of Madrid, José María Rodríguez Ortiz, who was the co-authored one of the papers, one of the works that will be presented today in one of the sessions. Paco had the privilege of working with Professor Rodríguez Ortiz on several occasions, and most notably during the construction of the metro in Quito, in Ecuador. So may this word serve as a tribute to his professional and personal career, and may he rest in peace. And then Paco wants to welcome all of our speakers who are taking part both from Spain and Australia. Yeah, we thank you all for taking part. And Paco has acknowledged the high technical quality of their work. As for the technical topics for the webinar, they're really around safety of tailings dams. And these dams are very unique in the sense that they are dynamic, evolving infrastructures, which, well, their construction goes on for decades. And really the geometry and the characteristics and their behavior patterns evolve over time. And in addition, the stored element is not just water; it's really tailings, and they're not harmless. So, all things considered, historically, the tailings dams have not been really given the importance they deserve, especially in Europe. I think this is quite a hot topic, maybe in South America. I think also probably in Australia, certainly way more relevant than in Spain, and I think in general in Europe. But these dams are very sensitive to severe accidents and major incidents. So for this reason, it's of the utmost interest to really review in this webinar some of the singular failure mechanisms, notably flow liquefaction. And really the procedures to improve the control of these tailings dams by means of proper surveillance, proper design, management of seepage and key variables, and then we'll review some historical cases. The sessions will be both in English and Spanish, depending on the preference of the speaker, of the panelist. And so we'll start off with the Australian presentations because of the time zone. I'll just introduce our speakers, and then we'll follow after a short break with the presentations from Spain, which will be coordinated by Paco. And finally, we'll have this panel discussion. And we'll try and bring up some of the hot topics. So we hope that well, this webinar is of your interest, and this will be recorded. So hopefully, we'll be able to disseminate the knowledge on YouTube, on SPANCOLD's YouTube channel after that, and the presentations will be available for everybody as well. And so if I'm not mistaken, it's my turn. So I will do an introduction of tailings dams, safety and surveillance. I'll try and really touch quite a few topics that we can then bring up during the panel discussion at the end. So I'll start sharing my screen. So hopefully you can see my screen now. I'll go really quickly over lots of different topics. So hopefully you will be okay, because I'll throw quite a few subjects and topics, but which some of them will be further developed during the webinar. And I'll just try really like do a quick review and an introduction to tailings dams. So tailings really are really a waste product out of the processing of mineral ores. So in the mines, we have the ores, we extract that material, we process that to try and extract the minerals we want from the ore, but that process is never efficient, 100% efficient. Actually, in many cases, more than 99% of the material is really a waste. So, and it's not really possible to reclaim all the chemicals, metals, minerals, organics, processed water that's used in that the processing of the mineral ores. And so that waste material comes out as a slurry that we essentially store in a storage facility, which is really the tailings dams. So dams are by far the most common and most efficient way of storing tailings. And tailings really usually come from like a flotation process that's used for the separation of the minerals. And in general, a normal tailings slurry has a concentration, a solids concentration that typically goes from somewhere from 15 to 50% of solids concentration. We'll see that really it's a wide range depending on how we process the tailings. So we'll get to that in a few minutes. And if we have a look at the typical mining operation, we can see that within the different tasks and operations in a mining facility, we extract the mineral ore so that that ore can be processed. We can have quite some significant amount of tailings, this waste, tens of thousands of tons every day, and we store that waste material, those tailings, we store them in our tailings dams. So depending on the type of dam, also tailings can be very critical to the dam behavior. So when we talk about tailings, we're really considering a broad range, a broad array of materials. In the ICOLD Bulletin 181 from 2016, it's an excellent bulletin, and we have a nice classification of tailings. You can see that they range from coarse materials with very low plasticity to very ultra fine tailings with high plasticity. And in essence, we want to know about the geotechnical nature of the tailings, which is really defined by the particle size distribution and the plasticity of the clay fraction. We want to know about the in situ condition, the state, which is really determined by the density, the water content, the stiffness, and the strength of the tailings. And then we want to know about the structure, because based on the way the tailings are disposed of, we're going to have interlayering, we're going to have segregation, trying to promote drainage. So we're going to have really a non-homogeneous material. And so apart from this classification, this ICOLD Bulletin 181 gives us some interesting charts that really gives us this solids concentration and then the settling time. So if we just grab a jar and we fill it up with tailings, based on the time it takes for the material to settle, we can have an idea of the type of tailings that we have. And then void ratio. So another important thing is really the void ratio of the tailings and the mean effective stress. Within this region where we have the void ratio and the effective stresses, we're going to really have the critical state line, the critical state locus. We'll talk about that. So this is an important one as well. And if we go to the good old plasticity chart, where we have the A line, U line, we can see how these different types of tailings sit. And apart from the size distribution and the plasticity, Carl Torsagi in 1948, in his famous textbook, he talked about this liquidity index, which is the water content minus a plasticity limit divided by the plasticity index. So when this liquidity index goes beyond 1, so it's bigger than 1, he said that the material tended to flow. So this is an important thing, because materials with a high liquidity index, 1.5 to 2, these are going to be very prone to flow liquefaction. Then if we move on to the dams and the construction methods we have for tailings dams, we have the infamous upstream construction, where really the center line of the dam is moving upstream into the pound, into the reservoir. We start off with a starter dam, which is at the downstream toe of the dam wall, and then we have stages, and as we store more tailings in the reservoir, this is raising, and we have these stages. And the thing with upstream tailings dams is that really this non-consolidated tailings material that can be saturated is really part of the dam. So that's why really the characterization of these tailings is critical when we have upstream tailings dams. And then we can resort to like cyclones to try and segregate and promote drainage. Carlos, ¿puedes mutear? Sorry, Carlos. I don't know if Alberto can mute. Okay. Alberto, I don't know if you can mute, but Carlos is, if you can mute his. Okay, thank you. So apart from, these upstream tailings dams are really critical because many of the flow liquefaction and failures that the famous ones, the flow liquefaction crisis, Feijão, Fundão, Feijão is Brumadinho, really upstream tailings dams. And then we have also downstream center line, which is different variations. And we can even have dams that are really constructed out of waste rock. So like typical water dams, which obviously are safer, both for static and seismic loadings. But these are the very dangerous one. By the way, these are banned in Chile and Peru. So Chile and Peru, this type of tailings dams are banned. Also, we have the water management. Tailings dams and water is a very important component of tailings dams. I will not really elaborate on this because David Brett will talk about water management more in depth during his session. But yeah, water is a critical component of tailings dams. Then we have different ways of going about with the disposal of tailings. So the classical one is really spigoting. So spigoting, in essence, is a single point or multiple points with spigoting, where we have essentially pipes connected to one distribution pipeline that is really conveying the tailings from the processing area into the tailings, into the impoundment, into the reservoir. So you can see that we have like a beach. We try and have that, and this is the typical way of tailings disposal. We may have a solids content that may range from 15, 20, 25% of solids concentration. Then we have the cyclone. So cycloning is used at many tailings facilities. With the cyclones, essentially, we try to separate the coarse particles from the fine particles in the slurry to promote drainage. And so we can have a set of cyclones, and this is like a central type. And you see that the beach that I talked about in this case is very prominent. But yeah, trying to segregate the material to promote drainage. And then, of course, we have other types of tailings disposal, thickening, that's been used since the mid-90s. And thickening really involves the recovery of a portion of the processed water. And out of that, we really go from that 15, 20 to 30% of solids concentration. And we can typically go from somewhere between 55 to 70% with a thickening process. So the ballpark of 60%. So we improve the condition of the tailings. Of course, that's more expensive. Filtering is even more expensive, and filtering, the filtration with pressure or vacuum filters can really move the solids concentration all the way up to 80, 88%. It's more expensive, but because of environmental constraints and so lately you can see more filtering. Even this like mud farming of amphirols that you can find somewhere here in some places here in Australia. And then also you've seen before with the spigoting, we have a closed tailings facility with the pipes disposing of the tailings. And this is like a central tailings discharge where you have the thickened tailings coming out from the center, and we have this beaches coming down, and then it's like a round shape tailings facility, tailings dam. Okay, so what about the tailings dams failures and safety? So with tailings dams, we could say that we have a big challenge because in the last decades, we have different references, but in essence, the number of tailings facilities constructed has really, it's a threefold increase in the last decades. And if we go to the annual probability of failure, it's 2 orders of magnitude higher than a typical water dam. So if for a typical dam and hydropower dam, we have an average annual probability of failure of 10 to the minus 4, some cases 10 to the minus 5. With tailings dams, it's usually like 2 orders of magnitude higher. So 10 to the minus 2. It's different depending on the reference, but that's the idea. 2 orders of magnitude higher probability of annual probability of failure for tailings dams as opposed to typical water dams, and then many of these failures. If we go for the flow liquefaction, which is a very prominent failure mode, almost 90% of the flow liquefaction failures are really related to the upstream construction method. Others really within the foundation. So let's not forget as well the foundation. Actually, Atnalcoyar, Cadia. So some of these failures are really beginning in the foundation. So we have flow liquefaction in the foundation, and that may propagate into the tailings, but it really begins in the foundation. So the foundation is also critical. And this upstream construction method is a big challenge because we have thousands of tailings dams all over the world with the upstream construction, and we can change that and try to move on to maybe a central line or downstream construction for closure and deal with that. But that's a big challenge that we have. And if we look at the evolution of the number of failures, the yearly number of failures, and this is the released volume released millions of cubic meters, we can see a decline in the number of failures following the technological advances. So in the 70s with drainage, we can see a slight decline. Then with control of runoff water, we can then see a slight decline in the number of failures per year. And then lately, with a risk-informed approach, new standards, undrained analysis, we can also see a decline. But then, of course, you can see this big jump in the volume released with Feijão, Brumadinho, and really the flow liquefaction crisis that led to the to the standards and the guidelines we have nowadays. So when it comes to tailings dam safety, we have the global industry standards that came out in 2020. We have the ANCOLD guidelines that are being updated. This is really in this image, the version from revision from 2019 has been updated, but then also the ICOLD dam safety guidelines from 2022. And what we find in these updated or these dam safety guidelines is really this risk-informed approach, really starting from planning. So really having in mind the closure of the tailings, the dams. So these dams go on with our construction process for decades, and eventually we close them. So the mining operation are closed, is over, but we have the tailings dams with the tailings, and we still have to take care of the tailings dams. And so we need to have a really safe design for that closure. And we should really think of that from the onset and not really put off or push off the investment until the end. Then in these documents, we also have ideas about when to move on from the limit equilibrium to the non-linear deformation analysis. So we can maybe talk about this during the panel discussion for the proper design of tailings dams. Now, when we talk about dam safety and tailings dam safety, so what is dam safety? Well, dam safety in essence is really a process. It's really, if we go to the ICOLD guidelines, dam safety is really a dam safety management system that has to be transparent, that has to be open to reviews and audits, that it really involves the organization. So really clearly stated objectives and policies, a management framework, an organization with roles, responsibilities, proper resources, training programs, and then being transparent. And it's really an ongoing, proactive process from the pre-operational stages to then the operational stages. And we find this proactive approach both like in classic ICOLD guidelines and then in the mining industry as well. So within this dam safety management framework, these processes, then we also have the dam surveillance, which is one of the cornerstones of dam safety. So within a dam safety program, we're going to find dam surveillance, which is really a series of concomitant, redundant activities based around inspections. So visual inspections, but then inspections, let's say with instrumentation, like monitoring, either with instruments or with surveys, like topographical, geophysical surveys, and control of the water and in our dam, and really using all this data to turn it into useful information about the safety levels in our dams, just to take action, and also recording, so the storage of all this data that's been turned into information by properly trained professionals. So all of this is part of the surveillance. So instrumentation is only just one of the pillars of dam surveillance, which really, you can see, encompasses, it's a broader scope within a dam safety program, which obviously also includes emergency preparedness and really a regulatory framework, and eventually having safe facilities. And when we talk about dam surveillance, we have different types of data. So visual inspections are going to give us one type of data. The monitoring and instrumentation, we're going to have a different type of data, including the metadata with the location of the instruments, if there's any maintenance going on, the constants, the formula. Campaigns are going to give us data, the topographical geodetic campaigns, but then also any type of geophysical, INSAR, GPS campaigns, and testing. So within the ICOLD approach to dam surveillance, testing is part of dam surveillance. So all the in situ CPT, seismic CPT, core drilling, even lab testing, all of that is going to be part of the dam surveillance system. And when we talk about instrumentation, so one of the big pillars of dam surveillance Ralph Peck, back in the day, talked about the importance of answering a specific question when we install an instrument. So in essence, failure modes. So do we know about the failure modes and the mechanisms, the failure mechanisms? Are we really answering the right question? Of course, proper installation, so procurement and how we procure the installation of dam surveillance systems is important. And then the human factor. So the human factor is key, both to foresee and to interpret the data and really turn the data into useful information about safety levels in our facilities. So once we have this introduction, dam safety, historical failures, what are the key challenges in tailings dams? Well, one of the key challenges we have in tailings dams is really the failure modes, and of course they're associated, linked to liquefaction of the materials. Starting with flow liquefaction. We can have flow liquefaction with saturated or nearly saturated loose materials. So anywhere from 80–85% of saturation. The soil, eventually those air bubbles are going to dissolve, and really the soil, the tailings are going to behave like a fluid, and completely saturated if we have flow liquefaction. And then we can have a significant strength loss. So when these materials are subjected to shear stresses, they can withstand a deviatoric stress, but then we can have a big drop in the shear stresses and deviatoric stresses that the soil can't withstand, and that's the strength loss. That's the softening that we often talk about. If that happens with large deformations and very quickly, then we talk about brittle behavior. So we'll come back to this idea. Strength loss and brittle behavior. We'll come back to this in a minute. So really the volume of saturated, potentially contractive material that we have in our tailings is going to govern the overall stability of our tailings dam. So if we have enough volume of these saturated loose materials with a contractive behavior, then we can have a problem, and we can really have global instability, both in the tailings dam and the foundation. Of course, the deviatoric, the shear stresses have to be large, bigger than the undrained strength with large deformations. And we need some triggers. We'll talk about the triggers in a minute. And of course, we need a geometry that allows really this global instability. And you can see that many of these triggers have to do with vibrations, small earthquakes. So that's why we want to talk about flow liquefaction. And that's why saying static liquefaction can be a little bit misleading because of these triggers. And of course, we can also have the cyclic dynamic liquefaction. When we have an earthquake, we can have alternating stresses and a poor pressure buildup, which can really eventually reach a critical condition, and really at that point the soil behaves like a fluid. So let's go back to the triggers. If we go to the Fei Zhao Brumadinho expert panel, we find in there some really a good list of potential triggers for flow liquefaction, going from really a rapid loading, such as the construction of new layers of tailings, cyclic loading, such as small earthquakes or blasting, or repeated blasting, that can really trigger flow liquefaction. Even unloading, such as rising water levels within our soils and materials, or even in the foundation, so localized loss of strength due to inflows coming from the underground springs. Of course, internal erosion, human interaction when we're drilling and doing stuff in our tailings dams, loss of the negative pore pressures that we have in the unsaturated areas above the water level, the surface, phreatic surface, internal creep. So all of these are triggers, potential triggers for flow liquefaction, and this really makes the problem really complex. And now, what is this flow liquefaction, brittle, strength loss? What is so in the ICOLD bulletin from 2022? We find this excellent plot where we have this normalized shear stress. So it goes from 1 to 0. So we have a shear strength. So how much the load, the deviatoric stresses we can apply to our soil, and we can have a drop in the strength. So from this peak, we can go down even almost to 0 resistance. So at this point, the soil is going to be flowing like a fluid. And then we can have somewhere in between a partial 20% loss of that shear strength, maybe 40%. So based on that, we talk about the strength loss index, this IB. So if IB is 60%, means that we're going to have a reduction of 60% in the maximum deviatoric stresses that the soil can withstand. And then when we talk about brittle behavior and brittle failure, then we're introducing the deformations. If we have a material with high plasticity, it's going to have a progressive failure. It's going to take, we're going to have a lot of deformations before we get to this strength loss. If we have a sand with a lower plasticity, maybe that's going to happen more quickly. So that's really how brittle the material can be. And in this technical guideline from 2022 from the ICOLD Technical Committee L, we also have a diagram flow that tells us when really to move to non-linear deformation analysis and when to really not resort to the limit equilibrium good approach. So we move on. Let's talk about now earthquakes. So the cyclic liquefaction. So if we go back in 1978 in Japan, some of these tailings dams failed. And one interesting thing is one of those dikes really failed one day after the main shock. So nowadays, we now know that this has a lot to do with pore pressure buildup. But well, it's evolved. So we really didn't know much about that, and now we know what this can happen with the dynamic one. And if we go to the basics of how the soil is behaving, let me share with you 3 slides, really courtesy of Mike Jeffries, who earlier this year shared with me some of his slides and his Excel macros for the triaxial test and critical state soil mechanics. So we have the old model where we have a shear box with a normal stresses and a shear stresses, and then if we plot how that is evolving as we shear that box, we have friction, cohesion. So that's the old model. Then even from 2 centuries ago, we know the dilation. So this idea from Reynolds of the spheres and what happens when we are loading a soil, if it has a dilative behavior, we're going to have a volume increase that develops negative pore pressure when these structures, the spheres, are really interlocking with one another. Or we can have a contractive behavior if we're compressing the structure of the soil, and we have a volume. In this case, the volume is decreasing, and we're going to have a pore pressure buildup. If we move on to the Taylor Bishop from 1950, when they went to the shear boxes, again, we have these normal stresses and the shear stresses. And so we apply these shear stresses, and we have deformation, so movement of the upper part of the box. And we find this peak in the stresses the soil can withstand, which are really due to the dilation, this interlocking, they call it back in the day. And eventually we're going to have deformations with really no increase in the shear stresses with a frictional component. And so when we go to these good old shear boxes with the shear stresses, the normal stresses, friction, dilation, which is really distortion, the distortion of the box. If we move that into the triaxial approach, with triaxial testing, we're going to talk about eta, which is really the deviatoric stresses divided by the mean stresses instead of the other one. We're going to talk about dilation, dilatancy, which is really the volumetric and distortional deformations. And then the frictional component is going to be really when this line, if we plot eta, so these the stresses with dilatancy, it's really a line. When that line crosses the vertical axis, we have this critical friction ratio, and we have also Nova's volumetric coupling parameter, which is really the slope of that line. But so it's really turned this idea of the friction, dilation, and the stresses into triaxial. And if we move on into the critical state theory from Bean and Jeffries, and again, this is courtesy of Mike Jeffries, instead of the Casagrande approach that goes from this plot to the void ratio versus mean stresses, critical state theory begins with this axiom that every soil has this critical state locus that separates the contractive behavior. So remember, decrease in volume and development of pore pressures from this dilative behavior. And each soil has it's very specific critical state line that separates those behaviors. And we use void ratio and mean stresses. And we use this state parameter. So we have a certain void ratio in our soil, and how far that is from the critical state void ratio is the state parameter. And then the second axiom is, of course, we're going to have this distortional strain that it's going to tend to go to infinite. So we're going to have a lot of deformation when we really get to this critical state. So this parameter equals 0, essentially we are in the critical state void ratio. With this, we come up with a differential equation, and we go back to the previous equation. Remember, with the line and the frictional and the dilatancy, and really critical state puts all together. So this image again from Mike Jeffries, we can really put it all together. So the triaxial testing, the odometer test put together with really a yield surface that separates elastic from plastic behavior, the flow rule. It's like the equivalent to the Poisson ratio. So how the material is going to deform, have deformations, and the hardening law, which is how this yield surface is going to evolve from one tensional state to eventually get to the critical state. Again, we have the friction ratio, dilatancy. So we put it all together. And again, the state parameter is the void ratio we have and how far we are from the critical state, and we can have saturated or unsaturated loading. And so critical state theory puts all of that together. So that's an important thing. And this is really incorporated into the non-linear deformations on plaxes for these last almost 10 years now. They all have these constitutive models built in. Let's move on. Another idea is how the fines content really impacts this. So remember, with the void ratio and the mean stresses, we're going to have this critical state locus that separates the contractive and dilative behavior. But that line is going to change based on the fines content. So this is an important thing to account for. Another idea, another challenge we have is going from one specific point in our tailings dam, for which if we can manage to get an undisturbed sample and take it to the lab, then we can test that. In the lab, we can have this deviatoric stresses and the strains deformations. So these contractive behaviors, we're going to reach a peak in the strength, and then we're going to have a massive drop in the strength with large deformation. If we go to the PQ plot, you can see that these contractive materials are going to reach this peak in the deviatoric stresses they can withstand, and then they're going to drop massively until they reach this critical state locus. And the challenge is knowing how much of that material we have, and if it's big enough to really trigger an instability in the dam and its foundation. This representation is taken really from the Fei Zhao Brumadinho expert panel. So that's, and then Robertson has used it afterwards. It's very useful, in my opinion, to see these different behaviors. So hopefully you're not blind color, but the contractive, so strain softening, is really when we have these deviatoric stresses, we get to a peak and then we have a massive drop. And this is really the residual or post-liquefaction strength. So essentially, it's after we've gone over this peak and we have this massive reduction in the deviatoric stresses that the soil can withstand. So this is the strength loss. And if we have large strains, then it's the brittleness. In the PQ region, you can see we're going to go this way and then drop massively into the critical state locus. And if we go to the void ratio and mean effective stresses, of course, we're going to have this contractive area, dilative, and we're going to have this buildup of pore pressures. And again, the critical parameter here that really governs that. So the importance of the residual strength. So remember this residual strength, liquefied and drained, which really happens after these massive deformations have taken place. If we move on to how these soils behave when they're loaded dynamically, if we have an earthquake, and this is really from a lab test, we're going to have these alternating stresses, but this is really the envelope, the static envelope. So we're always going to be within the static envelope, even if we have dynamic loading. In the lab, we're also going to have a pre-liquefied condition. We're going to have these cycles. This is really from a lab test, but in a real earthquake, we're going to have these alternating stresses, eventually reduction, and it's going to be alternating here. But the idea is with a post-liquefied condition, we're going to have large strains, large deformations. Again, with the cyclic resistance, we can go for in the lab and see the number of cycles that it takes for a soil sample to liquefy, and that changes with the relative density and with the fines content. You can see this is the cyclic stress ratio, CSR, which really represents the seismic load that is applied to the soil. And if we go from the lab to the field, then we have these beautiful simplified methods from, seed anhydrous from the 70s, and that use the CPT, or in this case is SPT, but in essence, they give us out of CPT SPT testing in situ. They give us an idea of the residual strength that we have based on the results of those CPTs, SPT tests. Bear in mind that we can have amplification of the accelerations in our tailings dams. So a typical tailings dam that is like 50 meters, 40 meters high may have a natural period of 0.3, 0.5 seconds. A higher tailings dam, like 100-meter high, maybe we're going to have a natural period of 1 second. So if we go to the spectral accelerations, we can have very important amplification. So we really have to account for that from the peak ground acceleration up to the acceleration we can have in our dam. We can have an amplification. We got to watch out for that. And also, if we use the simplified methods, the static bias, because these methods assume like a horizontal terrain, and of course, in our dams we have the slopes. So we have to watch out for these, because when we compute the factor of safety against liquefaction, we can have important reductions in that factor of safety if we account for this amplification and that static bias. And so finally, how do we deal with this brittle behavior? Well, number one thing, we need to identify these saturated brittle materials. And for that, we really use CPT, seismic CPT use that gives us the P wave. So these seismic CPTs, they can really let us know if we have saturated materials. We're going to have typical velocities of 1,500 meters per second if we have somewhere from 85 to 100% of saturation. But that P wave velocity is going to drop drastically, maybe to 500 meters per second if the material is not saturated. So this can really give us a really good clue. We have to be careful with piezometers, because unless we have several piezometers in the same vertical line, maybe we're not going to be able to find unsaturated materials or the position of the phreatic surface. Maybe we can talk about this during the panel discussion. We have to be careful with that. And of course, for extreme consequence dams, we really need to decide when to move from the limit equilibrium approach to the nonlinear deformation analysis. We move on. So how can we assess the susceptibility of our soils, of tailings dams to liquefaction? In situ, we use the CPT. So this is the chart from Professor Robertson, where we have the normalized cone resistance and the friction ratio and these different regions. You can see this is, again, the residual liquefied undrained strength in relationship to the vertical mean stresses. You can see that go all the way down to 0.05, all of these contractive materials. And when we go to a real tailings dams and we have hundreds of samples and we plot that into that same chart, you can see that we can have a significant amount of samples that are potentially liquefiable and contractive. So how to deal with these? Maybe we can talk about this in the panel discussion. Also, out of those CPTs, so we can assess this residual liquefied undrained strength. We can assess that out of the tests, and we can even use the Bean and Jeffries representation when we have the state parameter. You can see anywhere below minus 0.05 and positive values of the state parameter. So all of this is going to be potentially liquefiable materials. And if we plot the factor of safety against liquefaction with depth, you can see that we have a significant amount that can be liquefiable. So how to deal with this, what to do with this in real examples. Again, we can talk about this in the panel discussion. I'm finishing now. So dam break-in assessments, how these tailings dams break, the velocity and the extent of the tailings flow really depends on whether we have a lot of water if we have a water erosion during like a rainy day extreme flood event, or if we have flow liquefaction of the tailings, we can eventually have all the tailings removed, like in Brumadinho or in Alcoyat, or maybe we can have a very dry and limited flow, as in Cadia or Sullivan Mine. So that really depends on the rheology. So dam break assessments for tailings dams are very important and challenging. And then, can we really foresee these brittle failure mechanisms? And so after the failure of Brumadinho, we had these publications of the inverse velocity of how many days it takes for the tailings dam to have a deformation of 1 millimeter, and how when that inverse velocity gets to 0, eventually that coincides with the collapse of the dam. But again, the expert panel in Brumadinho did not really believe that that would have been really able to foresee the failure of the dam. Even if we go back again from the expert panel report, which is an excellent document, 6 months before the failure, we have some seismic activity associated with that drilling of sub-horizontal drains in Brumadinho, in the Feijão tailings dam, which is quite similar to the seismic event that the actual failure of the tailings dam really triggered. So it's very challenging. In Alcoyat, the dam was inspected the afternoon before we had that failure in the foundation that eventually propagated to the tailings, and Alcoyat really downstream. So not upstream construction, downstream construction, but it fell in the foundation and propagated into the tailings and some inclinometers. But can we really, would be able really to foresee that and this brittle mechanism and take action? Let's discuss that in the panel. With internal erosion, of course, this is an important trigger and also failure mechanism for tailings dams. Some of the things we want to look for: the exit gradients, the ratio of the pore pressures, and if we have seepage and we can collect that seepage, and of course, if we can do some geophysical campaigns, and how important things to look for as well. So finally, to finish this long introduction, how do we assess the behavior? And this is taken again from Professor Robertson, and also in the guidelines is also mentioned. We have the prescriptive design, so the traditional approach based on factors of safety and single values for the parameters. Sometimes we find designs with 2 or 3 decimals, that may give a false sense of certainty when we really have a lot of uncertainty. And definitely, I mean, this is not suitable if we have potential brittle failure modes. Then we have the precautionary design, which is that prescriptive, the factors of safety combined with the observational method, where we have instrumentation, and we can have like an action plan based on how the instrumentation is evolving. But this is not really appropriate for brittle failure modes. Then we have the performance-based design, which is it's really an extension of the observational method. So we include modeling, we include these modern remote sensing automated systems and numerical modeling that focuses on key parameters, but this is not appropriate when brittle failure modes are present. And then within, for instance, the ICOLD 2022 guidelines on tailings dam safety, this performance-based risk-informed approach is mentioned. In essence, so I think the game changer here is really the failure modes, identifying the failure modes. For each one of these failure modes, have performance parameters that can be really quantified, and having thresholds, appropriate trigger, action response plan, the TARPs, to take action maybe if the pore pressures go beyond a certain level, or the deformation goes beyond a certain level. and really monitoring and documenting all of that, with combining that with the modeling and comparing with the expected behavior, and really taking action and being proactive. So that's, I think, at the essence with this game changer of the failure modes. Now, when we talk about analyzing the instrumentation data, of course, we can use statistical models, deterministic models, hybrid models, machine learning techniques. Maybe we can talk about this during the panel discussion. These are very, very powerful tools. And again, really deciding when we need to move from the limit equilibrium modeling to the nonlinear deformation analysis that uses a triaxial and in situ testing, probably driven by the consequence assessment. So extreme and very high consequence tailings dams probably need to move on to the nonlinear deformation analysis. And finally, some conclusions. So monitoring is a key component of dam surveillance, closely linked to these action plans, triggering action response plans, and both used to confirm and really foresee any changes. We can talk about full implementation of the observational method for non-brittle failure modes, and a conservative design criteria when we have brittle failure modes, assuming we can have flow liquefaction and these residual strengths going on. Of course, that performance-based, risk-informed, safe design we've just talked about. Being careful about the digital transformation. We maybe have a lot of data, but maybe less information. So something to think about. The importance of the material assessment, understanding the material we have in our tailings, and proper characterization of the tailings, and how difficult it is really to foresee these flow liquefaction failures. But in any case, we need redundant, automated, and distributed monitoring technologies in real time, combined with TARPs and including INSAR, automated in-place inclinometers, seismic network arrays of piezometers, fiber optics. Really, finally, really focusing on the instrumentation of pinpoint potentially saturated and liquefied areas within our tailings. So that's this long introduction. I hope I've not burnt you out with the presentation. I've really thrown lots of topics and subjects. I've just finished on time, so we're good to move on, and we can save some of those ideas for the panel discussion. And we'll move on now to a presentation done by Brett Stephens, who is the chairman of the ANCOLD Technical Committee on tailings dams. And so Brett has extensive experience and is a knowledgeable professional on the tailings dams and dam safety. And he's going to talk about the Australian practice, the ANCOLD guidelines. So Brett, the floor is yours.
Thanks, Manuel. I'm just going to try and move something around. I'm not looking backwards. Can you see my presentation, Manuel? Thank you. So look, my one's fairly simple. So I'm just going to talk to the group about the update to the tailings dam guidance that I'm working with a group of professionals on. So not many slides, pretty straightforward. And what we're trying to do is update our documents with all of these new advances in the tailings technology and the learnings we've had recently, which is not a trivial thing. So I'll just talk about the group. I'll talk about the guidance and the context. I'll probably show what we're trying to do. And we're right in the middle of writing the documents at the moment. So there's not a lot to share, but we'll give you some of our thoughts and approaches and probably give you a context of what we're trying to do in ANCOLD on this. So we started doing the tailings guidance. So I'll look at the work in progress and really information that we've done. So we've gone out and talked to stakeholders. ANCOLD's a member-based organisation, so we've gone out to a number of groups and asked them what things are working in the guidance that you have at the moment, and what things are not, and what things do you need additional information on. We did that about 2 years ago. So the group started in 2021. So I have to give credit. This is the group who donate a lot of their time to this undertaking. And we all assumed that we're going to get this thing done in a couple of years. We're now in year 3, and we think if we're very lucky, we'll have something out to the review group next year. And I'll explain why that's happened, and we think it's the right reasons. But we have a bunch of people from different stakeholder groups, academia, consulting, industry, and we're very fortunate in that the peer review group is almost entirely the group that wrote the original guidance documents in 2012 and updated them in 2016 and 2019. So it's not often you get the advantage of taking the formative group that did that, and they're going to come and help us and provide their experience. So one of the benefits of ANCOLD. So the guidance was last revised in 2019, and that really was a response to a number of the dam failures, of course, in 2015 and 19. But we also had the Australian seismic guidance was updated in 2018, and we changed all of the seismic ground motion prediction equations. And so as a result of that, that was updated. And obviously since 2019, we've had ICOLD Bulletin 194, we've had GISTM come in, we've ICM guides, TSM, and a number of other documents that have added to the practice. So what we want to be doing is taking opportunity to include these guidance and predominantly Bulletin 194, which is a great document, and I'm looking forward to seeing it finally published, and including that in the ANCOLD framework. So that's really the brief. This is the slide you saw earlier from Angus, and it's a pretty important slide for us because one of the people asked me, are we going to change the guidelines in ANCOLD to reflect GISTM? And the answer is pretty simple, no. The Australian guideline documents are based on, significant and high ABC consequence dams and extreme, and there's a reason for that, and it's all within these other guidance. So we're not going to change those guidelines, and I'm pretty sure that the tailings industry is used to working and flipping between reports for GISTM and ANCOLD. So we want to piggyback off the other guidance, and so as Angus mentioned, this dam safety management, which is currently in revision. One of the members of our group is actually on that group, and he reports in to that group. And what we're trying to do is make sure that we balance what we're putting in our guideline with the new guidelines. So, but first and foremost, when you're designing a tailings dam, it needs to be designed in accordance with the dam safety management guidance and all of the other guidelines in ANCOLD. And then in addition to that, the tailings dam is going to add all of these additional specific design elements that need to be in addition to that. So fundamentally, when you're designing a dam in Australia, just like you do now, after these guidelines come out, you will need to have a copy of dam safety management in your hand and also the tailings guidelines in order to design the dam. That's probably a pretty interesting key point to know, because both of those manuals will be relevant for a tailings dam design. So, and of course, we're hoping to include a lot of these technical bulletins. So examples such that Manuel was showing all of these evolving practices and technical improvements we have. It's just not possible when you have a manual that takes so long to produce. So what we're planning to do with this new electronic guidance system we have, where the documents are available immediately on a website, is to put these technical bulletins out there at a much faster rate so that we can address these technical advances and give more guidance in a more timely manner to our members and stakeholders in the group. So just a quick one. This is a pretty poor diagram, but it just talks about how the current guideline was put together and it's phase driven. And it's quite good because it explains to people the steps that need to happen in the design process, and it moves people through, pre-feasibility, planning, pre-feasibility, design, and operation. And it talks about all the elements. And it was a great step forward in tailings design. I think it's been the yardstick by which all of these things have been driven. And I guess that was good, and we're hoping to build on that. But we're saying it's really a phase design, and one of the things that we talked about when we did this is really the design of tailings dam as identified by most people who talk about it. It's a cycle. We talk about some dams now that have been in service, major extreme hazard dams that have been in service for over 60 or 70 years and continue to be built higher and bigger and continuously. So you don't design a dam that big once, you do it almost every year, and you're checking it and you're improving it. So what we want to do is we want to have this framework that embeds a damming cycle of design. You plan, do, check, act, and that cycle continues through the life of the project and responds to the environment and the materials and the construction and the behavior of the dam that we monitor. And if we do it well, we should be well ahead of it. So we're predictive, not reactive, which I think is one of the key things we need to be thinking about. So when we talked about this, and we spent a lot of time doing it as a group, is we talked about this performance envelope. And this is really coming out of Bulletin 194, where we have this risk-based informed design. The performance envelope is really the goal that we set for the dam. So when we do the performance envelope, what are the legal commitments for the dam? What is the owner's commitments? What's closure look like? How are we going to close it? What's the landform? What's the storage? Do we expect variations in the ore body? Do we expect variations in the amount we do? Is there a chance that the client may want to increase the production by 30 or 40% because that's a business imperative? So they're the things that need to be put in there, and those performance envelopes need to be instilled in the design right up front. And then the key thing about performance envelopes for us is that really leads to a performance indicator. So it's not really a performance indicator if it's not measurable. So, and that's something that we'll probably start talking about when we go to the thing. But I guess the other thing is that when we don't actually meet our performance envelope, we rectify. And so one of the real problems about the observational approach, which Peck talked about all through the 70s and the 80s, is that you may have an observational method, but if you have no chance to rectify the design, you can't use the observational method. And some of these facilities just get too big too quickly, or they don't have contractors. Or if you think about dams somewhere in Northern Australia, they're 1,000 miles away from a contractor. And if you need something happening tomorrow, if the fleet and the people and the materials aren't there, then the observational approach just doesn't apply. So I'll move on. So really, this is the new metric that we've put in the guideline. It's the first pass of it. And I guess I've just sort of thrown a red line around this, which is really meant to be a Deming circle. So the key thing here is we need to define the performance envelope. What do we really want as a goal for the dam? How is it meant to operate? When does it start? When does it finish? What are the things that need to happen? All these things are inputs into it, owners' commitments, site constraints, and there's a myriad of other things that need to go in. And all of these elements in there are part of the design process in order to meet that design performance envelope. And it's a bit abstract, and it takes a bit of talking around to get an understanding of it. But really what it's really doing is it's installing that process that was in the old guidance and putting in a cycle, right? And going and making sure that people come back and do that. And I think for most people who work in tailings, that's intuitive and not a very big leap. I guess we're just instilling that in the document at the moment, and it's probably going to be a bit of a leap and a fair bit of debate about how we do that. So probably caused a lot of comments in the thing. So So what's really going to change in the progress? So I keep telling people a lot of the practice that we're doing now is not going to change materially. I think we're going to give clearer guidance and more updated and specific guidance to the things we asked. We've talked about closure and risk and dam break governance. I think those things are clearly going to be updated to reflect the current, the current practice and a little bit clearer, so there's less confusion about how we adopt them. And these are really born about by the questionnaires that were issued in 2022. So we've gone back to our membership. We will then go back, write this up, we'll get it out to the peer group, and then we'll put it back in the membership again and make sure that's good before we get it out. We want to, as you said, we want to link it to the DSM guidance, and that's really to limit repetition in the guidelines. If DSM's already told people how they need to design a dam and given really good guidance or the risk assessments there, we don't want to repeat that in ANCOLD. We think we just want to focus it and say, if you want to do a risk assessment, the risk assessment guidelines tell you how to do it. Here's some additional framework to apply that in a tailings dam scenario we think you should consider. And so really what we're trying to do is build on the existing ANCOLD documents. I guess one of the questions we've been talked about is GISTM, and really we're just going to continue to focus on the technical aspects of the tailings dam. We'll talk about governance, but really governance around dam safety and technical design of these dams, which is really in the wheelhouse of what ANCOLD's doing. And we're probably going to move a long way to incorporating most of the really good work of Bulletin 194. And there's going to be exceptions. And I think David's going to talk about those in the water practice, specifically around some of the things we do in Australia, which is unique to Australia and the conditions and the climate, which is obvious. But most of our things are going to be there. So here's just a list of the guidance. I'm not going to go through it, but people wanted more discussion on and a little bit more clear guidance. Some people found it confusing or ambiguous. So we're going to go and look at that. One of the things we will be focusing on is really risk assessment. We're going to push down and really promote risk-based informed design, because we see that now in our practice, that the more we use risk assessment in tailings dam design, given all the complexity, the better our engineering outcomes are and the more informed our operations become. So I think that's one of the big pushes from ANCOLD, that we keep pushing towards risk-informed engineering design and risk assessment and the value of it. And the more you use risk assessment, the more you'll see the value of it. And I think this is my last slide. So really just, we're going to update the tailings guidance. We'll link it with the current guidance. I think we're just following on from Angus's initial talk. We're going to be looking at both dam safety management, the DSM that's in revision. Hopefully it will be out next year or soon after, and promote risk-informed design processes that we already use. We want to have it process-driven and defined on this performance envelope, and making sure that we really have clear goals, and the clear goals move to a measurable performance indicator, and that measurable performance indicator moves into how we operate, how we check, and how we confirm we met the safety. And I think that's really the clarity that we want to have. So going out there and just throwing instruments in and thinking you're safe doesn't help. It's as Manuel said, you need to understand why you're measuring it, what's driving it, and we believe risk assessment helps you understand your risks and move yourself down the line so that you're preemptive that. So we've set a whole bunch of tasks for ourselves that we're trying to do, and we're hoping to have something out to our peer reviewers next year. That's our goal, but we've got a lot of hoops to jump through. So that's my last slide, Manuel.
Excellent. Thank you so much, Brett. And I think you, apart from the showing us the evolution of the ANCOLD guidelines, you've really, you've brought up those key subjects. The envelope, the risk-informed approach, and I think during the panel discussion we can go back to that, because it's really the key and really the practice is really evolving, because when do risk assessment to tailings dams, yeah, we go for the event trees, and then we can even use the criticality approach, because sometimes the fully probabilistic approach, it may not make that sense, but really the orders of magnitude and analyzing the event trees, like you said, it really enhances the safety management, and it really enhances and informs the dam safety approach.
Yeah.
Absolutely.
I think in mining they're very used to using these the FN curves from the quantitative risk assessments, and they're now starting to lean on them as something that allows them to really put a basis in their decisions on why they're doing something, because these things are measurable. And I think that helps everybody, the designers, the owners, and the stakeholders see where the value in doing certain things lies, right? So
it really does. Hopefully we can go back to that during the panel discussion. Okay, thank you so much, Brett. And we're gonna move on now with David Brett, who will talk about water management for tailings dams. So, well, David also chaired that ANCOLD committee, and he's been involved with the ICOLD technical committee on tailings dams for, I mean, forever, really. And so, yeah, David, the experience and background that David has is just outstanding, you can imagine. So, David, the floor is yours.
Thanks, Manuel. I'm speaking to you from Pondicherry in India. I've made an early start to heading to ICOLD, and you can see I'm not as formal as some of the presenters. I've got my frangipani necklace they put on me as I arrived at the hotel a little while ago. So
it's beautiful.
Everything...
It's beautiful.
I'll just try and share my screen. Oh. Okay.
Okay, and if you go to full mode.
Right, how's that looking?
Good. It's slide number 4, but
okay.
we can see it. So
No,
if you
sorry.
go back to the beginning.
I'll go back. There we go. How's that?
It's all good. Okay.
All right, thanks. So yeah, I'm going to talk to you today about water management, and I guess to me, water is pretty much the most important thing we should be considering on our tailings dams. It's a very important part of it. And, you know, are we really managers of tailings or managers of water? And, you know, what we see is a tailings beach in a facility looks pretty solid, but it's pretty much most of it's water. And even after we've added the tailings to a beach and let it dry for a while, it's going to be maybe 65% solids by weight, but it's still 60% water. And even after it's got pretty dense down in the dam, it's still potentially around about 50% still water. And this water is potentially contaminated. It may not be able to be released into the environment easily. So that's the water in the actual tailings, but we also have large catchment areas on our dams, so we have to manage stormwater as well. So, you know, we're getting water from the tailings slurry and also from the environment. So I think Mount Polly failure was a bit of a watershed for tailings dam safety, and the traditional owners got an expert panel together to review the failure, and they came up with some pretty interesting conclusions that have been probably very, very big effect on our engineering that we do now, because it was a very open process, and so all the data was available for people to see. And what this expert panel noticed was that over 46 years in British Columbia, there'd been 7 major dam failures, which is quite a lot for a pretty reasonably small place. It's like one state of Canada. And so that ended up with a failure rate, if you looked at the number of tailings dams they had in British Columbia and applied that failure rate, it would be suggesting that they're likely to have a failure once every 5 years. And to them, they judged that this was a intolerable risk for the community. And so something pretty dramatic had to be done to move towards a very low risk and preferably zero risk. And so they introduced the ideas of best applicable practices and best available technology. Best applicable practices would be things like improved corporate responsibility, independent review boards, much better governance systems that we're talking about today with engineers of record and that sort of thing. But the examples of best available technology were really mainly associated with water, because the Mount Polly failure was notable because of the amount of water that was on the dam. And whilst the failure caused by an unknown foundation condition, if it hadn't been for the water in the dam, the consequences of the failure would be very much reduced. So the idea of getting rid of water was what they saw as reducing the risk to the dams. And what they really came up with that potentially the best available technology at the time was filtering of tailings to produce a dry stacking concept. So the idea of dry stacking was that there wouldn't be significant water in the tailings. They'd be unsaturated and they could be compacted. And they also suggested a reduction in the use of water covers. I mean, this is a bit more controversial, I suppose. Water covers in some instances are actually very good for environmental situation of stopping oxidation of potentially acid forming tailings. But I think if you interpret it as the reduction in the use of water cover rather than covers, like water cover is removing the water so that we don't have that extra material to be released in a failure, and also lead to release of eroded tailings materials. And then because there was this pretty clear relationship between water storage and breach volume. So these are a few of the tailings dam failures that have been happened around the world over a number of years, and you can see these are probably pretty. I'm not sure where this came from, to be honest, but it was probably a bit of selecting the right examples to give you the data. But the far right was Stava in Italy. Mount Polly is that green one in the middle of the screen there. So you can see that the failures that had a very large surface area of water on the dam ended up releasing a much greater proportion of their tailings in the failure. So the message from Mount Polly: reduced water storage on the dam and also reduced water in the tailings mass. So basically that means increasing the density. So first of all, I want to talk about reducing water storage on the TSF. There's several factors that mean we want to store water on the dam. First of all, the water quality and the reluctance to release it. So there could be environmental restrictions on the ability to release water because of the water quality and the effect on the environment. But also there's often a site water balance issue where the mine wants to keep water on the dam so they can recycle it and use it and store water during wet times so they can use it during the dry times. So really the ideal solution from my point of view would be to have an off dam storage, so independent of the tailings dam. And yeah, but that would mean you'd have to have a pretty robust decant system so we can get the water easily off the dam. And oops, sorry. And even when we have a storm event, the water was able to go off to an off-site dam, and if it's got environmental restrictions, well, then that dam could be used to store the water. But that the off-storage dam would be potentially a lower consequence classification dam because there wouldn't be the risk of the catastrophic tailings release. But if we can't afford to do that, or it's not possible to have an off-dam storage for the environmental water, well, then the less ideal option is to limit the water storage to reduce the risk. And to do that, we have to balance the environmental impact of the water release with the increased risk of the dam failing and releasing tailings in a catastrophic event. And this is what a lot of our guidelines are aimed at doing. So in our ICOLD Bulletin 194, for example, we have this diagram of the sort of water management aspects of the dam. And I've just started playing Indian music in the bar here. I hope you can't hear it. I might have to go and ask them to turn it off, but hopefully it's okay. So anyway, we've got our decant system, which could be a gravity pipe or a pump system. And we've got a normal operating water level and a maximum operating water level. Oh, sorry, the music's distracted me. And then we have a range of operating water levels that would account for normal weather effects. And above that, we've got an environmental design flood storage, which is meant to be this water we want to store a certain flood event so that we don't release environmentally contaminated water. And then above that, we've got our inflow design, which is our stormwater flow, which we need to go through our spillway, and that gives us the design basis for the spillway. But there's quite a lot of pressure on people not to have spillways. In certain parts of Australia, for example, the regulator requires a no-spill dam. And really, to me, that is fundamentally increasing the potential risk of the dam to try and store these floods. And I'll talk a little bit about that as we go. So the environmental design flood needs to consider factors such as the water quality that could be released and regulatory requirements. So they should be based on what the environmental effect of that water could be if it was released in the environment. And obviously important things would be the frequency and duration of those overflow events, the effect of mixing in the environment downstream of the dam and what that effect is on the environment. And also, pretty importantly, the public perception of having a spill. But I guess in my mind, we have to balance the public perception and the environmental issues against the increased risk of a catastrophic failure and how that would be so much worse. So in ANCOLD, we do have this consequence-based method, and we've looked at the potential consequences of dam failure, and we use a similar method for flood design and earthquake design, but for the environmental flood, we're really only looking at what would happen if we spilled some water over a spillway into the environment, and typically that would not involve any loss of life or major infrastructure damage or potentially some health of people, but mostly it's really going to be the environmental damage that would be the consequence. So we look at that environmental consequence and decide whether it's minor, medium, major, or catastrophic, and we have definitions of what those different effects are. And once we've decided on the worst case of damage and loss, we go and look at loss of life. And for the spill consequence classification, really, there shouldn't be any risk to life. So we'd be in that top bracket, and we will then assign a dam spill consequence classification according to the damage and loss to the environment, which in most cases for tailings dams would probably be low to significant. There could be some high, and if the water is very good quality, well, it might be minor, but most of the dams would end up in that medium to major classification. And then we give some guidance on how you would then decide what floods to use in those situations. So environmental flood design for a low consequence, you'd look at a 1 in 5 wet season. For significant, it'd be a 1 in 10 wet season, and for a high, it'd be a 1 in 100 wet season, which is a sort of an idea of what storage you should be providing on your dam that doesn't go over the spillway. And then also we have this extreme storm allowance. So typically for most of the dams, that's going to be a 1 in 100 72-hour flood. The inflow design flood uses a similar method. And in ANCOLD, we have for a low consequence classification, we use a 1 in 100 flood for the spillway design. For significant, we use a 1 in 1,000, but as soon as the consequence classification goes to high, and we have several levels of high in our consequence classification system, but as soon as we go to the lowest level of high, we are using a 1 in 100,000 flood plus wave run up. Or alternatively, we can use a PMF without any wave run up. And then we go to the extreme consequence classification, we'd be looking at the PMF, but also looking at any other extra freeboard we should be providing over the spillway to have a larger flood capacity. So it's a pretty straightforward system, and it does vary slightly from the GISTM and the ICOLD Bulletin 194. Bulletin 194 was really developed by all the team on our ICOLD committee. Probably the most input was from Australia and Canada, but other countries as well. And so there's always a bit of debate when you try to get agreement in ICOLD on what exactly you should do. So consequently, our consequence classification system in the ICOLD bulletin is a bit biased towards the Canadian system, and that's then transformed into the GISTM, who took an early version from our ICOLD committee to develop the one for the GISTM. But even though we've got some minor differences, I think that overall the key thing is we're trying to get some fairly conservative flood design criteria, because flood design is got a lot of uncertainty, as Manuel was talking about earlier. In just overall tailings design there's a lot of uncertainty we need to think of. So to me, a very important thing is when people start trying to store all the water in the dam, not have a spillway or have a very large storage capacity, which means you can run the risk of ending up with a lot of water on the dam. And it's very hard to come up with a design basis to look at how you should select the storage capacity you should provide in your dam to avoid overtopping. And I think you have to consider extreme storms and multiple storms. You also got to look at your emergency response capability, how you can get water out of the dam, because during some of these extreme storm events, people are not going to be able to service pumps or fuel pumps or repair power lines that are down, and people won't even be able to get to the sites because of the traffic or the road conditions and flooding and stuff like that, and people are not even going to want to go to work. They're going to be more interested in protecting their families and things like that. So I think the whole question of storing water in dam is very difficult, and we need to think it through pretty carefully. So in ANCOLD, we do try to address this by saying that a spillway should be provided unless it's inconceivable that the dam could overtop. But I think we probably didn't really take enough care in thinking about this, because I think we should have added also that failure by piping is inconceivable. As soon as we get water level up high in the dam, particularly in upstream dams or even centerline dams that might not have really been designed to contain water, we really, there's a big risk of failure if the water level starts to encroach on the crest and is actually in contact with the outside wall. So when I'm trying to design a spillway system, I'm trying to control the invert of the spillway to be related to the tailings beach rather than the crest of the dam, so that we are actually having a basin of tailings holding the water rather than let the water encroach outside the tailings basin. Hopefully that's understandable what I'm talking about. But I just
David,
sorry.
you have a couple of minutes, so well,
Yep, okay.
you can have a bit more time, but just be
Yep,
aware
no
of the
worries.
timing.
The other aspect is water that's in the tailings, and if you look at the tailings when they're in the plant, we typically got a 20% solids slurry, and that's got 4 tons of water for every ton of tailings. And as we go through thickeners and then onto the beach, we're losing water. But even after we get to the beach, there's still potentially 60% water that we're dealing with. And you know, where does that go? If you don't get it out on the beach, it's going to end up having loose, low density tailings at the surface. And this diagram is meant to show that the structure in the middle there is a chart showing the low density at the top and high density at the bottom. And to get from the low density to the high density, we have to have consolidation and water being squeezed out of the tailings. So we end up with a lot of water that we have to deal with that really potentially hasn't been allowed for. So we've done some beach trials in some of our mines around. This one's up in the north of Northern Territory of Australia, where we've gone out on the beach over time and measured the density and the water content. And we found that evaporation from a tailings beach is only really effective for the first 10 to 14 days. After that, it becomes very ineffective. So we can look at a density curve for tailings, and we can find that as we're converting from a wet slurry to a dry beach, we can coming off, and we can get to a limit that is typically when the beach dries out, it just gets to a point and it won't go any further. But if we add the next stage of, if we were able to take some more water out and compact the tailings, we can get to our typical soil compaction curve where we've got a maximum dry density and an optimum moisture content. And that's really what we should be trying to achieve in our tailings. And in Australia, Manuel did mention the amphi-rolls. There are some sites where we've got machines that can go out into sloppy tailings and traffic on them and create drainage furrows and then fluff up the tailings to get increased drying. And we can get low ground pressure dozers, amphibious excavators out on tailings, and we can actually end up with if we're doing careful beaching, a good rise rate that's not too fast, we put the right equipment on there and do it properly like a quality controlled earthworks, we can get density that is equivalent to what we would be able to get through dry stacking of a filtered tailings. So can we improve on dam water management? I think we've got a lot of improvement we can do. We can reduce water storage on tailings dams, be realistic about the environmental issues and balance that with the risk of catastrophic failure. Provide carefully designed spillways so we don't end up having too much water in the dam that can get close to the embankments and risk overtopping or piping failures. And mechanical compaction is something that is being used, and with people on all sorts of different mine sites can use it if we think about it carefully. That's all I've got, Manuel, so wasn't that far off, hopefully. Thank you.
Yeah, thank you so much, David. So interesting, and I think apart from the technologies you've shown, I think we can go back and revisit during the panel discussion some of the design approaches and the differences between the different guidelines, because that's really really interesting. It really is. So thank you so much for that presentation. And okay. So before the break, we're going to move on to the last of the Australian value share presentations with Edgar Salas. is really he's the engineer of EOR, engineer of record for Cadia. And so Edgar has 17, 18 years of experience as an engineering geologist, and he's worked in South Africa, in Papua New Guinea, and then in Australia for many years. And he really has massive experience when dealing with mining operation facilities, and he's the engineer of record for Cadia, so that's the case history that he's going to share with us. So Edgar, adelante. The floor is yours.
Thank you. Thank you, Manuel. And yeah, basically, I'm just going to go through the findings of the RTRB report. The panel then did the investigation of the failure because I'm not allowed to share anything else that is not already available to the public. Here we go. Let me see. Can you see my screen, Manuel? You're checking, yep. Then here we go. I'm just going to go with a brief introduction just to let people know where Cadia Mine is. But basically, that there is Australia, and here we have Sydney. Then, if you have been here before or you have an idea where Sydney is, it's a small town called Orange. Is to the west of Sydney. Is part of the state of New South Wales. Within 20 minutes of that town is a place called Cadia Valley Operations. Cadia Mine is a gold producer. Is mostly a block cave operation, and they've been there for almost now close to 30 years. In terms of the site, this is an old photo, but give you a good idea. Then this is Cadia pit. Is the way how they used to explode the gold. Is no longer in use. Then we move to the URCT dam, which is a water dam, and that water is mostly used for the processing of the tailings. Then we have the Northern TSF, which is what we call it the NTSF dam, which is the dam that suffered failure back in 2018. And then downstream of that dam, we have the STSF of the Southern TSF. These two dams are quite similar. They sort of a twin brothers. A little bit of more of the background of the NTSF now. The NTSF was commissioned back in 98. The dam started as a conventional dam. That basically means it's a water dam type of design with a clay blanket, filters, and so on. Then the dam was basically built to 50 meters in high, and it was built as a downstream dam. Then that was followed by stage 2A, which is pretty much a downstream construction from stage 1. That was finished in 2000, and then the stage 2 was divided into 2B and 2B1 and 2B2, and that was completed in 2003. After that, the dam, basically the geometry changed to a center line for stage 3, and that was completed in 2005. And then from that point forward, the dam was moved into upstream construction, and then we have a total of 10 stages before the dam fell back in 2018. Then what the dam looks like internally, then as was going through the table before, then this is what we call the starter dam of the stage 1. That was followed by this sort of stage 2, which it was built downstream in 2 parts. And then the stage 3, which is this tiny here center line. After that, as I mentioned before, it follows 10 stages upstream, most of them being 3 meters in high, a part of stage 6, which it was actually 6, until the top of stage 10. During the design process of stage 10, the designer back then realized that the factors of safety through that connection in here were quite low. Then basically a key reason for that is that and back to what Manuel was talking about, is the host within the tailings actually changed. The host in the tailings here was quite coarse. Then the CPT results showed that the material was somehow better than they thought it will be. When they put the stage 10, then the findings of the CPT basically shows that it was not. The material was liquefiable and brittle. Then the designer identified that they need to put that batteries in here And then to put that batteries, they also identified, and they need to put these other batteries to be sure that the dam was stable under static conditions. Then based on that, then they went into the construction of these two buttresses that I just showed. Then and this is pretty much the alignment for the construction of that buttress, and we're going to focus on this area here, which is where the dam failure happened. Part of the design of the construction process requires the foundation excavation of certain areas to a competent ground. And this in here, you can basically see in here then is where a big chunk of the excavation it was planned to happen in that area. Then as the construction was pretty much in progress, the morning of March the 9th, back in 2018, part of the pre-construction or the requires the construction manager or the construction supervisor to inspect the working area. Then you can see here is a gap in here, and that is because they were placing these sort of a batteries. Then as they were doing the morning inspection, they identified some tension cracks on the portions of the dam. And I'm going to show you that in here. This is basically the morning of the failure. And then they identify some sort of a tension cracks, large tension cracks on stage 8 and 7 of the NTSF. Then you can see here that is the buttress that was pretty much on the construction. You don't see that in here because pretty much this one here is looking to the eastern side of the dam, when this one is looking to the west. The buttress was coming from the west to the east. That was the sequence, the construction sequence. And then you can see these large tension cracks, and this is pretty much where this one of the supervisors was walking and inspecting these cracks. Then down into the toe, they identify a toe heave, basically evidence that the dam was rotating and basically moving. That happened the same day in the morning, and basically late that day, late in the afternoon, then basically the dam fell. Then this photo here was taken on the 10th. The dam fell on March the 9th, about 7:30. Is more or less the time that is you can it was recorded and the dam fell. Then something interesting to here to notice is, and I'm going through some sort of a photo, is the dam basically some sort of a slump or rotate, and then you can basically, if you have a look at the photo, you can follow pretty much what the embankment used to be. It's almost like the dam was pushed. The ITRB mentioned how similar this dam failure was to Los Frailes in Spain. Then as the days basically pass, then the liquefaction start actually happening, and the dams start liquefying and start overtopping that sort of a mini dam that was built after the dam fell. And that is quite interesting, and it's a key characteristic that the ITRB they're trying to explain with a lot of the modeling and the investigation that they did. Touching again in that point, I'm pretty sure that a lot of you have seen this on LinkedIn. After the failure, it was a company that started basically presenting some data on how the insider managed to see the failure happening. In fairness, and I'm looking at this data now, and if you were basically building a dam and you were moving a lot of things around, and you have a point in here, then you can quickly infer that this was something that was sort of expected. That was within what you would expect, or it might be noise. You can see it went up, then it went down, then another point. Then by the time that this was clear, this was taken within 15 days apart. Then and then back then, Kedia was not using this technology. Then back to are we able to see this or not? Are we able to predict this type of failure? We understand what the dam performance used to be if the designer were expecting to see this movement, and if it went a little bit out of what they were expecting to see, if that was enough to stop construction. All these questions that we need to ask ourselves as designers, as owners of dams. It's certainly not easy to see this coming. In terms of the investigation results, I'm just going to go briefly through the geological conditions in here. Then this area of New South Wales is quite complex in terms of geology. It's a lot of volcanism, and most of the soils in here are residual soils. They are not basically transported soil or sedimentary soils. They pretty much like a saprolites. They go through a severe leaching. They stay in there. This area is semi-dry. Then you go and do an geotechnical investigation and you get refusal. You actually go and have a look at these soils and you won't imagine that these materials can become really weak. Then in here you can see this yellow here is a basal flow. Here in Australia, which is similar to parts of South Africa, the tertiary basals typically they hide really paleo channels because it's quite young, and is quite young geological unit. Then below that is what they call forest volcanics, which is all that pink. The vast majority of them is sitting on that, and it's a quite old soil, Paleozoic age soil, and has suffered a lot of weathering. Dry density is quite low. And the material is quite complex because it's coming from a volcanic origin, andesite, volcanic breccia, and so on. Then a really, really complex geology. In terms of what the RTRB defined to be the typical geological section through the failure, as I mentioned before, then we have the residual of the basal in there, like a cap, like a really nice cap hiding these paleoalluvials. Then you can actually see the baking zone, like as the basal flow through these old topography and gullies, then it basically you can see that soil in there. Then that follows all these classic profile of in situ residual soils. Then when we have the severe leaching is happening, pretty much like a soil-like material, and going to some sort of a rock of low density and then improve as you are going deeper. That is quite typical of these residual soils. I really like this is in here. This slide, as explains a little bit in terms of geomorphology, topography, how we end with that gully and with the geological conditions that are present in Kedia. Then we have a fault system. The Wimala formation is a sedimentary formation that is basically going up, and the forest volcanics going down. This one is the oldest one. This one is basically newer than this one. Then that create that sort of a profile in there where you have some sort of a creek or a gully. Then which it was basically filled with sediments, as you expect in this sort of environments. As the tertiary comes in and we start having all this volcanism, then that was pretty much covered by that tertiary basal. And the tertiary basal provide a really nice cap or protection to the paleoalluvial materials and also all these really saprolites. Then it's sort of you go there, do your geotech investigation, and you see this hard rock. Below the hard rock, then you have all these nasty soils that you might not be able to identify if you don't have that geology background. Then erosion keep going, and then we end with the topography that we have right now. That in here is where the dam is sitting, and it's sitting right there in that transition in between a really nice.
Oh, you're cutting off, Edgar. I think we lost Edgar.
It should be back. Don't know what happened there.
You're back.
Yeah.
You're back.
I'm sharing or I'm not sharing? I need to reshare. Yes.
No, we lost it. Mm-hmm.
Okay, let me just reshare. Here we go. Let me know if you can see that.
Yes, we're back.
Yeah,
back on track.
Then as this is a classic, I'll just the forest volcanics. This is the soil profile that it was highlighted by the ITRB, and you can see them basically really low density, dry density, and in there, and basically the Attenbergs of clays of high plasticity. Or then in terms of the grading, just for you to give an idea of what the grades look like, but yeah, a quite fine material, and in some of we can actually go to something not that fine, but just to give you some background of what the material looks like. In terms of the response of these materials to triaxial, then back to what Manuel was talking about, then you can see the material is quite brittle. Then the material with the 1.5 to 2%, you can actually see how the strain, you start losing all that strain really quick. and that basically is the main reason why this happened. The material is quite brittle. It was not recognized, and the loading of the embankment. If we have a look at the tailings, typical grade is on the tailings, and here we go here with the classic tailings, low plasticity, fine materials, 60 to 80% fines. CPT data from a location near to the failure, then the material, basically contractive, state parameter above 0.5, then potentially liquefiable, and all the nasty stuff that you basically see on tailings. Similar thing, the tailings at the typical state parameter, then quite brittle. Then you have all the right ingredients. You have brittle foundations, brittle tailings, a non-supported foundation, no identified foundation conditions because of the basal gap. And to basically for this dam to fail. Then the ITRB discussed different potential mechanisms. The one that they landed, which I agree with this, is we have some sort of a progressive shear failure that probably start at some point during the dam was being built. This embankment moved forward. When it moved forward, basically triggered liquefaction of the tailings. And I think that's quite evident in these photos that I show you, then where we have this first step, the dam basically, the foundation loses the strength, it moves forward, and that basically is followed by liquefaction of the tailings, and we end with that shape. Quickly going through the way how it was modeled, and they identified that this is probably happened or start happening in stage 6, where the stresses started exceeding what the soil was able to take, and progress with the construction of the different stages to a point where by the time that they were building the buttress in here and the excavation that was happening at the toe, then it was just completely pushed the dam to fail. In the findings, basically, as I mentioned before, it was that foundation material, and it was the accumulation of the formation of the construction, because they couldn't identify that the foundations were that brittle. Additional factors in there, the diming was quite high there, the phreatic levels in that area, and the excavation that was happening at the toe. I'm tracking good with time. Then just as acknowledgement, obviously for the panel, Mike, which I know quite well, Morgenstern, Dirk, and John. It was I sort of had the opportunity to work with them when they were doing the investigation, and I'm still in touch with Mike. It's quite good to pick his brain. And that's it, Manuel.
Yeah, thank you so much, Edgar. Muchas gracias. Really interesting and fascinating, and that's still under litigation, and so a lot of information cannot be disclosed. But I think it's one of those case histories out of that which we can really learn a ton of things. So hopefully in the panel discussion we can also revisit and go back to some of those interesting points from the Cadia case. Thank you so much.
You're
and
welcome.
we get to the break. So Paco, tenemos ahora un descanso.
Sí. Bueno, yo quería agradecerles a todos los ponentes, incluido a ti, la excelente calidad de las presentaciones que se han hecho. Y nada, decir que nos vemos en media hora, a las 11:15 hora española, y no sé exactamente, creo que son
sí, las 7:15.
19:15, las 7:15 hora.
Las 7:15 aquí, y luego
pues
tenemos a David Brett en la India, o sea que sí, estamos en diferentes zonas horarias, pero nos vemos en unos minutos. Muchas gracias, Paco, por tus generosas palabras. And on behalf of all the Australian panelists, thank you. Paco has thanked taking part. Thank you so much. Muchas gracias, Paco. Y nada, nos vemos entonces en aproximadamente 25 minutos, ¿no? 25 minutos estamos de vuelta. Y no sé si Alberto parará la grabación, pero nada, regresamos y retomaremos la parte española, celtibérica y luego el panel.
Ok.
Cuando queráis.
Perfecto.
Ya estamos en el aire.
Sí. Le doy a, si os parece, a compartir pantalla.
Bueno, la siguiente presentación la va a hacer Javier Moreno, que nos va a hablar del fenómeno de licuación por flujo, una aproximación teórica y práctica. Y creo que la va a hacer en español. Javier Moreno es doctor ingeniero de caminos y trabaja en el laboratorio de geotecnia del CEDEX aquí en Madrid. Cuando quieras.
Perfecto, muchas gracias, Paco. Bueno, pues previamente a mí me gusta siempre, antes de empezar a dar los 45 minutos de, no sé, nunca sé qué llamarle, si charla, no es una clase, es una conferencia tampoco, parece que la conferencia tiene un nombre como muy pomposo. A mí siempre me gusta hacer una especie de introducción, sobre todo filosófica, de lo que yo pienso un poco sobre el tema, ¿no? Entonces, en este caso de la licuación por flujo, es un tema que profesionalmente me surgió hace unos años y yo en muchos casos lo he visto como este paradigma que os traigo aquí. No sé si conocéis, bueno, es una fotografía muy famosa de la conferencia Solvay del 27 y estos son los grandes físicos que movieron desde entonces, ya habían movido anteriormente. Y bueno, está ahí Dirac, está Compton, por supuesto veis a Einstein, a Marie Curie. Y es un poco, yo lo quiero traer como paradigma de que a veces los técnicos, no me quiero poner al nivel de esta gente, por supuesto, aquí hay 19 premios Nobel, pero un poco a veces como que no sabemos o nos cuesta, digamos, nos quedamos con los conocimientos y nos cuesta transmitir al resto del colectivo que está muy interesado en las cosas que tratamos. A veces nos cuesta, digamos, no somos demasiado facilitadores de la labor. Y con esta idea me surgió la necesidad de preparar una clase para un máster que damos aquí en el CEDES, el máster de Mecánica de Suelo, Ingeniería de Cimentaciones. Llevamos muchos años dándolo y me plantearon dar una clase sobre licuación por flujo porque parece que está un poco, no de moda porque ya se estudia de hace tiempo, pero como más, está en la boca de más gente. Y entonces, cuando me puse a redactar, vi que había bastante, preguntaba a compañeros, preguntaba tal, cómo lo veían, tal, y entonces vi que había bastante, digamos, era como una especie como de algo como muy desconocido, ¿no? Entonces, me puse en contacto para mí con la persona que yo creo que desde el mundo es un puntero, no digo que sea el único, pero es bastante puntero, que es Peter Robertson, y le planteé la opción de, oye, mira, estoy preparando esto, estoy en el máster, quiero preparar un artículo donde se coja desde el principio hasta el final lo que es el proceso de la licuación por flujo, ¿vale? Y suele ser típico de las personas así, digamos, de generosas, de grandes conocimientos. Me dijo, todo lo que tú necesites lo vamos haciendo a medias, te voy pasando toda la información que quieras. Me parece perfecto. Ahí, como ponéis, estoy de acuerdo en la necesidad de educar cada vez más y más ingenieros del riesgo de la licuación por flujo. Y eso lo hicimos así y al año siguiente publiqué un artículo. No quiso publicarlo conmigo, lógicamente, me dijo, ponme en agradecimientos y suficiente para mí, ¿no? Entonces, todo lo que voy a hablar se desarrolla con más detalle en el artículo que está disponible en internet, en la revista Geotecnia de una revista portuguesa, y están todas las referencias y está todo tal. Y se puede seguir. Yo creo que la filosofía de este artículo es cojamos desde el principio, que es lo que vamos a ver ahora, desde el principio, y asistamos a aquella persona que está responsable de una explotación, asistamos a una persona que va a encargar un estudio, asistamos a esa persona para que ellos no serán expertos tras acabar de ver esta clase o tras acabar esta charla o escribir este artículo, pero lo que quiero es que sepan interpretar y tengan claro los conceptos básicos. Y una vez que se saben estos, cualquier artículo técnico será perfectamente conocido y se podrá, digamos, discutir. Esto hay que fijarse que pone una aproximación teórica y práctica. Yo no pretendo meter aquí temas de modelos constitutivos, de plasticidad generalizada, el PM4SAN. Eso lo dejo para otras, digamos, otro tipo de ingeniería. Yo lo he orientado desde un punto de vista mucho más, digamos, práctico, con unos conocimientos, digamos, técnicos básicos, pero que alguien, cualquier ingeniero, eso sí, que tenga unos mínimos conocimientos de mecánica del suelo, pueda analizar y pueda comprender de qué va el problema. ¿Y cómo está estructurado estos 45 minutos? Bueno, lo primero es, vamos a hacer, quiero ir de lo más básico, lógicamente cosas que conocemos todos, a algo un poco más evolucionado. Vamos a hablar del fenómeno de la ecuación, un marco conceptual, quiero hablar de eso y quiero ir a los principios más básicos que tengamos, lo que es el empaquetamiento de un volumen diferencial de suelo. Eso ya lo hemos visto, ha salido en imagen en la presentación anterior, de las 9, de Manuel. Vamos a hablar de los dos tipos de ecuación que hay, movilidad cíclica y la ecuación por flujo, y quiero distinguir para que se vea que es un fenómeno que no es lo mismo, pero que se puede interpretar bajo el mismo paraguas. Luego hablaré ya lo que es el motivo de esta charla, de este encuentro que tenemos, de la ecuación por flujo, qué materiales se producen, en qué material se produce. Discriminaré bastantes veces entre contractivo y licuable, no es lo mismo contractivo que licuable. Hablaremos lo que es la variable de estado que propuso Binney Jeffries en el 85, cómo la modificó Robertson en el 2017, porque se adecuaba más al comportamiento de los materiales, el estudio de los materiales licuables. Y hablaremos lo que es la evaluación de la pérdida de resistencia. Hablaremos luego cómo podemos ver si un suelo es susceptible a la ecuación por flujo. Hablaremos de ensayos de laboratorio, os daré mi opinión, hablaré rápidamente de lo que es el SPT para estos temas y nos centraré básicamente en el estudio del CPTU, que para mí creo que es el ensayo de laboratorio con más, que se usa más, ¿no? Más adecuado. Y luego, una vez que, hemos determinado que el material se va a licuar, bueno, pues, ¿qué resistencia le podemos asignar cuando ha licuado? Vale, ha licuado, sí. ¿Y cuánto resiste? ¿Vale? Pues vamos a hablar, aquí será un poco más controvertido, lo que pasa a profundidades reducidas o medias y la propuesta que hacen diversos autores para profundidades elevadas por encima de 40-50 metros de profundidad. Y una metodología, porque hasta aquí hemos hablado de, tenemos un depósito, vamos a analizar si tiene riesgo o no. Y ahora, en el apartado 6 rápidamente voy a hablar un poco de, bueno, vamos a hacer un depósito, no está hecho todavía, y cómo deberíamos hacerlo para evitar el problema de la licuación por flujo. Y finalmente unas conclusiones. ¿Vale? Bueno, pues si entramos en el primer apartado, esto ya lo conocemos todos, son los conceptos más básicos cuando empezamos en mecánica del suelo, es lo que vemos, tenemos un elemento diferencial del suelo, lo voy a pasar muy rápido. Bueno, si la arena está suelta y drenada o no está suficientemente saturada, bueno, pues cuando se le somete a un ciclo de corte, pues las partículas unas ocupan los espacios que habían dejado las otras partículas. No hay ningún problema, no se produce ningún fenómeno. El volumen final es más pequeño que el volumen inicial. Hasta aquí es muy sencillo. Pero si este mismo arena suelta la tenemos saturada, que es lo que nos va a pasar en los depósitos mineros, son sueltas por el modo de deposición que ya os ha planteado Manuel en la charla de las 9. Cuando está saturada, esa capacidad que tienen de ocupar los volúmenes de las otras está impedida por el agua que hay dentro. Entonces, ese espacio que demandan las partículas está ocupado, entonces el agua se defiende, por así decir, metiendo un incremento de presión intersticial que disminuye, por lo tanto, las resistencias porque disminuye las tensiones efectivas. ¿Vale? Y luego, el último caso, el ideal sería si tenemos una arena densa, pues tenemos al contrario, esa corte que le vamos a someter al suelo produce un aumento de, digamos, disminución del empaquetamiento, aumento de volumen y una disminución de tensiones de presiones de poro, con lo cual un incremento de tensiones efectivas, que nos dará, como sabemos las resistencias van con las tensiones efectivas, un aumento de tensiones efectivas, ¿vale? Aumentos de resistencia. Esto es muy, muy básico, pero de aquí va a salir todo el concepto. Nos vamos a 1936 con Casagrande, 3 años antes de la Segunda Guerra Mundial. Los sistemas para detección de incrementos de presión intersticial no están desarrollados y podemos hacer ensayos triaxiales drenados. Bueno, pues aquí vemos lo que tenemos todos en la cabeza. Tenemos un suelo denso, tenemos, a medida que aumentamos la deformación axial, tenemos un valor de pico y si aumentamos las deformaciones nos vamos a un valor residual que coincide con el valor que alcanzamos. Aquí tendríamos un proceso de reblandecimiento y aquí tendríamos un proceso de endurecimiento en un suelo flojo. Y si no fijamos, en vez de la tensión de corte y deformación axial, nos fijamos en el índice de huecos, tenemos este fenómeno. El suelo denso disminuye un poco los huecos y al final los aumenta, está el eje en sentido contrario, y el suelo flojo. Pero lo importante es que al final, esto ya lo sabemos, de muchos ensayos que disponemos, al final vamos a un estado de que se puede llamar de muchas maneras, de volumen constante, un ensayo de grandes deformaciones, etcétera, etcétera, ¿vale? Y van a morir, por así decir, al mismo punto los dos. Si hacemos eso con muchos ensayos, tendríamos unas trayectorias verticales en este diagrama, índice de huecos o en ordenadas, o tendríamos volúmenes, diferencias de volúmenes, y en abscisas tendríamos las tensiones efectivas. Como estamos en condiciones drenadas, pues las condiciones de confinamiento se permanecen. Con lo cual, en principio serían así. ¿Vale? Y la idea sería, bueno, si eso es en condiciones drenadas, en condiciones no drenadas no se produce variación del volumen, no se produce variación del índice de huecos. Luego, estimamos que debería ser así. Unas condiciones, unas trayectorias horizontales en vez de verticales. Bueno, eso lo vamos a ver que si, bueno, tenemos ensayos de Bien y Jeffries, que eso se produce, ¿vale? Tenemos trayectorias en ensayos no drenados horizontales, y si lo ponemos en vez de en unos ejes naturales, lo ponemos un eje logarítmico, el eje X lo hacemos logarítmico, bueno, pues se nos transforma bastante parecido, como se ve aquí, en una recta. Vale. Años más tarde, bueno, antes de nada, ya nos da una idea de que, hemos dicho antes, los suelos contractivos son los que podrán licuar. No siempre van a licuar, pero son los que podrán licuar. Y los suelos dilatantes densos no van a licuar. Es decir, ya nos da una idea de que en principio los de arriba serán susceptibles de licuar. En principio, los de abajo de la línea del estado crítico deberían no licuar. Hay, bueno, lo vamos a ver con lo que es el parámetro de estado, pero en principio nos deberíamos quedar con esta idea. Gonzalo Castro, ingeniero chileno, desarrolla sus trabajos en la Universidad de Harvard y en el 69 publica ensayos ya no drenados, ensayos triaxiales no drenados. Y en esta figura de Gonzalo Castro yo creo que podemos ver gran parte de lo que es el fenómeno de la ecuación por flujo. Os indico varias cosas que creo que hay que mirar. La primera es, vamos aumentando el esfuerzo desviador hasta que tenemos un pico y a partir, pongamos que es 225, y a partir de ahí, boom, nos vamos, perdemos una resistencia y nos vamos a la parte residual. Fijaos que podemos estar vamos a poner que es 80 de valor residual, tenemos 230, 225, es decir, hemos perdido más del 50% de resistencia. ¿Vale? Tenemos una pérdida muy rápida. Y fijaos que el incremento de presión de poro no es necesariamente, es decir, simétrico o no. Gran parte de la presión de poro final que vamos a tener, que es 350, gran parte por encima de la mitad, la hemos alcanzado hasta la resistencia al pico. Y luego el resto es un poquito más de incremento, el 30% más de incremento de presión de poro. Eso es importante, que tenemos que pensar ya que los suelos que van a licuar van a tener una muy importante pérdida de resistencia. Pero además una cosa que aquí tengo marcada es que esa pérdida de resistencia se produce de forma casi instantánea. Es decir, mientras que el desviador lo hemos ido introduciendo con una carga poco a poco, lo que es la pérdida de resistencia se produce de forma prácticamente instantánea. Bueno, esto es así siempre, esto es mentira, bueno, ahora os pongo unos vídeos de uno de los fallos que hubo en Fundao en el 2015 y estáis viendo aquí, está a escala, o sea, está el vídeo moviéndose, estamos subiendo ahora mismo, fijaos el colapso que va a tener aquí, estamos subiendo por esta rampa y ahora estamos a punto de llegar al pico y que se produzca el colapso. Ahora, en 0,18 segundos, en menos de un segundo, hemos perdido gran parte de la resistencia. ¿Vale? Es decir, lo que nos daba Gonzalo Castro es cierto. Hay materiales que en vez de ir perdiendo resistencia, la pierde de forma súbita. ¿Vale? Bueno, estos serían los materiales, por así decir, más peligrosos para nosotros. Son materiales que pierden mucha resistencia, ya estoy haciendo una especie de avance de lo que vamos a decir luego, y la pierden muy rápidamente, no nos va a dar tiempo a reaccionar. ¿Qué ha hecho la probeta? Bueno, pues lo que nos enseñaban los ensayos de Gonzalo Castro es, sufrimos un valor de pico y una vez que llega al punto B, máxima tensión desviadora, este camino, el BC, lo hace de forma instantánea. Si lo vemos en este gráfico, que es interesante, el PQ, empezamos, en este caso, una tensión isotrópica, vamos aumentando, hasta aquí sería un suelo contractivo, y si fuera un suelo contractivo, finalmente llegaríamos, por ejemplo, hasta aquí, ¿vale? O sea, iríamos con nuestra trayectoria de tensiones efectivas hasta tocar la línea de resistencia intrínseca, la que sea. No, en este caso no es contractivo solo. En este caso es un suelo licuable. Entonces, a partir del punto B, que es el punto que tiene la misma ordenada, va a caer de forma súbita hasta el punto C. ¿Vale? Si hacemos eso con más probetas, tendríamos todos uniendo los puntos donde la tensión desviadora es máxima, tendríamos esta línea. Esta línea es lo que se conoce como la superficie de licuación por flujo. ¿Todos los materiales tienen este comportamiento? No, solamente son los materiales licuables. ¿Vale? ¿Qué pasa si el material es denso? Pues el material es denso, llega a esta resistencia, la resistencia va a ser la misma, ¿vale? Pero no tiene una pérdida de resistencia. Estos tienen una pérdida de resistencia, estos no. Vale. Luego nos interesa saber que los materiales licuables, cuando tocan una superficie que tiene una inclinación, un ángulo de resistencia menor que el ángulo de resistencia, digamos, en condiciones ordenadas para pequeñas deformaciones, ¿vale? Pues nos interesa saber que como toque ese punto, esa línea, esa superficie, vamos a tener una pérdida súbita de resistencia. Vale. Con esto vamos a poder discriminar, con esta sencilla idea, vamos a poder discriminar fácilmente entre lo que el concepto de movilidad cíclica y el concepto de licuación por flujo. Y es ni más ni menos que saber en qué punto estamos. Vamos a ver un tema fundamental con este gráfico de Olson Star del 2003, que yo lo traigo siempre porque creo que es fundamental. Nosotros vamos a partir de un estado tensional, una tau, nuestro terreno, nuestra obra, nuestra geometría, nuestros pesos, nuestros materiales, implican que un punto determinado tenga una tensión tangencial tau. Y eso es lo que nos va a permitir decir si estamos en un tipo de licuación por movilidad cíclica o por licuación por flujo. Vale. Bueno, pues fijaos lo siguiente. Es importante, esto es fundamental que lo veamos claramente. O sea, si yo estoy en el punto A, es un material que va a ser licuable, con lo cual cuando toque mi trayectoria de tensiones a esta línea, que es la línea de lo que habíamos visto antes, la línea de la envolvente de licuación por flujo, tendré problemas y una vez que pase al B, caeré al C instantáneamente. Es decir, con una carga no drenada estática voy construyendo nuestro depósito, puede que en mi estado tensional A tengo una carga no drenada estática, se van produciendo excesos de presiones intersticiales, avanzo hacia el B y una vez que toco el B me voy al C. Pero, vale, una construcción rápida. Yo puedo decir, vale, de acuerdo, voy a ir construyendo muy despacio. No tiene, digamos, eso no tiene realidad práctica en lo que es la industria minera, pero bueno, podría ser. Yo voy a conseguirla. Vale, pero es que también puede haber una carga no drenada dinámica. Resulta que yo tengo mi estado tensional A' y resulta que yo voy a tener unas vibraciones en mi entorno por las explotaciones de mineras, porque hay un terremoto, por lo que sea, porque estoy haciendo un sondeo, lo que sea, y voy moviéndome, es una carga dinámica, no dejo disipación de presiones intersticiales, me estoy yendo hacia, y una vez que toque el E, hacia la línea de fluencia, digamos a la línea de licuación por flujo, me voy otra vez hacia C. Es decir, pueden ser cargas no drenadas estáticas y cargas no drenadas dinámicas, pero también pueden ser cargas debidas a variaciones de las tensiones efectivas debidas a ascensos del nivel freático. Es decir, yo no estoy controlando, no estoy haciendo nada a mi obra, no estoy subiendo el relleno, pero resulta que está lloviendo, no estoy controlando bien el nivel freático y me está ascendiendo, con lo cual, pongamos que la variación de tensiones verticales no están subiendo, las tensiones totales no están subiendo, pero como están subiendo el agua no lo estoy controlando bien, se me está yendo y me estoy disminuyendo las tensiones efectivas. Y una vez que toque el punto D, me voy otra vez al C. Es decir, tenemos muchas posibilidades de que tengamos el proceso de licuación por flujo. Pero fijaos que siempre partimos de puntos que tienen una característica, el A, el A'. La característica es que siempre están la tensión solicitante inicial, la tau, está por encima de la resistencia, por así decir, post-licuación. ¿Vale? Y eso es lo que nos va a definir los dos mundos. Si yo, mi estado tensional inicial, la tau, está en este triángulo azul y el suelo es licuable, puede que se produzca la licuación. Es decir, cuando por cualquiera de los tres motivos, cargas estáticas, cargas dinámicas o elevaciones del nivel freático, yo esté aquí, ¿vale? Lo que ocurrirá es que me iré al punto de estado de formación permanente, resistencia post-licuación, etc. Sin embargo, si yo estoy tangencialmente, inicialmente, en condiciones estáticas, por mi obra, por lo que sea, estoy en este punto, no pasa nada porque la resistencia que tendríamos digamos, a poslicuación será superior a la tau que solicita a ese material mi obra. Claro, no pasa nada, bueno, sí pasa algo. Pasa que si yo tengo un sismo, cuando tenemos movilidad cíclica, bueno, pues tenemos estos fenómenos, se van produciendo incrementos de presiones intersticiales, me estoy acercando hasta la línea de rotura y ya sabéis, se producen, digamos, el movimiento tensional, la trayectoria de tensiones. El stress path se produce así y bueno, tenemos en función del tipo de, si es más arenoso, tenemos las famosas curvas de la banana que tiene muy poca área, con lo cual amortigua muy poco. Si es arcilloso, tenemos más amortiguamiento. Pero cuando para el ciclo, cuando para la excitación, cuando para el sismo, se va a empezar a disipar esos excesos de presión intersticial y vamos a volver a nuestra situación estática que va a ser superior a la resistencia. Es decir, cuando deja de actuar la acción que produce la movilidad cíclica, parará la acción. Sí, tendremos muchos movimientos, tendremos muchas deformaciones, pero pararán. Mientras que en el caso de que si tenemos una licuación por flujo, una vez que se produce la rotura, las tensiones tangenciales de mi obra no es capaz de ser soportada por el terreno, porque esta tau que tengo aquí, ya el suelo no puede dármela, me la va a dar inferior, ¿vale? Es decir, con esta gráfica tenemos que tener claro cuándo es un tipo de licuación y cuando una licuación por flujo tenemos unas tensiones tangenciales superiores a la resistencia. Movilidad cíclica, no. Vale. Pues esto es lo que pasó en Niigata, en el 64, los famosos edificios de apartamentos cerca del río, se le pasó eso. Cuando paró, cuando son normalmente, fijaos que siempre suelen ser terrenos con muy poca pendiente, con lo cual tenemos muy poca tau que solicita. La tau estática que solicita es muy bajita. Vale. Ya hemos visto los dos tipos de licuación. Vamos a centrarnos ahora en la licuación por flujo. La licuación por flujo se ha dado varias oportunidades. Aquí tenemos unos casos, los que llamo yo ejemplos más importantes. Lógicamente, habrá casos que a cada uno le afecta de una manera u otra, bueno, pero esos están ahí, los de Stava, los de Sullivan, y los más famosos últimos, un poco así, han sido los de Fundao y los de Feijao. Os estoy poniendo el vídeo de Feijao. Fijaos, esto está un vídeo en tiempo real, esto está aquí los segundos. Fijaos cómo el comportamiento es totalmente repentino, totalmente brusco, ¿vale? Esto traerá unas connotaciones para lo que vamos a decir posteriormente, ¿vale? No se estaba haciendo nada, es una obra que se estaba, digamos, en fase de cierre, estaba sellándose, estaba analizándose, pero no había vibraciones, no había en principio, ¿de acuerdo? Vale. Entonces, ahora os propongo la definición que, en función de todos estos estudios, todos estos análisis, la pongo ahí que es mía, no es mía, sino que es la que yo propongo, no está sacada en ningún libro, pero creo que recoge todos los aspectos importantes que entiendo que es. ¿Qué es la licuación por flujo? Una pérdida súbita, muy rápida, os recuerdo lo de los 0,18 segundos de Gonzalo Castro, y muy notable, es decir, luego vamos a ver, a mí si pierde la resistencia del suelo el 10%, no se va a producir licuación por flujo. Tiene que ser una pérdida súbita y muy notable de la resistencia de los suelos. Y, muy importante, que tiene asociados unos movimientos indefinidos, siempre que la más inestable tenga salida cinemática. Es decir, no es que ha parado el sismo, ha parado la licuación por flujo. No, se ha producido la licuación por flujo y la masa deslizante se acomodará a la geometría de la ladera, se acomodará a la geometría del valle y hasta que tenga inercia bajará por el valle. ¿Estas inestabilidades cómo son? Pues estas inestabilidades tienen una serie de características comunes que son las que ahí pongo. Bueno, pues habéis visto antes, las alteraciones del entorno no tienen que ser muy importantes, son elevaciones del nivel freático, son pequeñas vibraciones, yo estoy construyendo, bueno, todos estos depósitos normalmente no estamos en un estado hidrostático, sino que tenemos un exceso ya de presión intersticial por la ejecución misma y el relleno. Bueno, pues son alteraciones del entorno muy reducidas. Son roturas, en general, sin previo aviso. Y voy a poner una frase que a mí me duele ponerla, porque yo soy el responsable del CEDES, de todo el tema del área de auscultación y ensayo de campo, pero la auscultación en la obra no es válida y pongo con reservas. A ver, hay que tener las obras auscultadas y medidas y tal, pero no pensemos que nos va a avisar con un inclinómetro que eso se está empezando. No, o sea, no es un movimiento normal de deformaciones de varios centímetros al año, varios 30 centímetros. No, no va a ser así, va a ser muy brusco. Son roturas progresivas y muy rápidas y en general movilizan una parte de material que se licúa. No se puede licuar solo un poquito, sino que a lo mejor el trigger, el que dispara, es una zona pequeña de material, pero en general requiere grandes volúmenes de material licuado. ¿Y cómo son los materiales que licúan? Pues ahí los tenemos. Las características más comunes suelen ser suelos muy jóvenes, pocos años, 30, 40, 50 años, con muy poca plasticidad o ninguna plasticidad, normalmente consolidados, y todos estos materiales que licúan son contractivos. Ojo, no todos los materiales contractivos no son licuables, pero todos los materiales licuables sí son contractivos. En general, los casos que se conocen, y eso será lo que discutiremos al final, se suelen producir a tensiones efectivas bajitas, en las partes superiores, 30-40 metros del relleno, y tenemos unas pérdidas de resistencia muy notables. Bueno, ¿y estos materiales cómo podemos caracterizarlos? ¿Qué nombre y apellidos le podemos poner? Bueno, pues ya os he comentado antes, Bean Jeffries en el 85 proponen establecer lo que sería el parámetro de estado, que sería ni más ni menos en la gráfica que hemos visto al principio, pues sería establecer si yo mido la diferencia entre el estado, el índice de huecos inicial y el estado en estado crítico, ¿vale? Steady state, estado grandes deformaciones, pues si yo tomo esta distancia de mi punto inicial a la línea de estado crítico, bueno, pues tendría, lógicamente, si está por encima, hemos dicho que tenemos problemas de licuación, pues tendríamos un valor de parámetro de estado superior a 0. Y si estamos por debajo, tendríamos parámetros de estado inferior a 0. Eso es la opción que plantean Bean y Jeffries en el 85. Pero surge la idea de Robertson en el 2017 que dice, bueno, si yo tengo el mismo material que antes, fijaos que está en la misma posición, pero tengo una línea de estado crítico mucho más tumbada, tendría la misma distancia de las tensiones de mi deformación inicial a la SS, es decir, tendríamos el mismo parámetro de estado. Sin embargo, en un caso y en otro, se puede ver que en un material estaríamos, en un caso, la resistencia, habríamos perdido una cierta resistencia y en este caso habríamos tenido una pérdida de resistencia muy fuerte, ¿vale? Entonces, Robertson propone modificar y no usar tanto la distancia en vertical, sino usar esta distancia en vertical, porque nos da una idea mejor si el material es, como en este caso, esta trayectoria de tensión es licuada, frente a si el material es un material contractivo, ¿vale? Trayectoria licuada, material es contractivo. Bueno, entonces lo que parece que nos interesa más es medir la distancia en horizontal, desde el punto inicial de presiones hasta el punto final de presiones en estado crítico. Si se hace esto en distintos ensayos, en función de las presiones intersticiales, bueno, esto está en muchos artículos, se ve como, lógicamente, me da igual hablar de índice de huecos que densidad relativa, ¿vale? Se observa que los valores obtenidos en los laboratorios tienen un tramo que parecería ser bastante recto, ¿vale? Pero es bastante recto, y esto es importante, es bastante recto en tramos hasta presiones del orden de 2, 3, al principio se decía 2 atmósferas, ahora se habla de 3 atmósferas, 3, 4 atmósferas, pero en un tramo de presiones no muy elevadas, pero a partir de unas presiones más elevadas, estas curvas tienen un cambio muy severo de inclinación, tienen una curvatura importante. Esto ya lo vio Boulanger a partir de las formulaciones, esto es algo que se conocía a partir de la formulación de Bolton, que relacionaba la dilatancia con eran ensayos de laboratorio que tenía Bolton, recopiló un montón de ensayos de laboratorio y vio cómo influía las presiones de confinamiento en la dilatancia y la densidad relativa. Bueno, pues Boulanger aplica el criterio y dice, bueno, si para obtener estas curvas de estado crítico, la dilatancia voy a considerar que el estado crítico es 0, con lo cual voy a aplicar las formulaciones de Bolton a ver qué curvas me da. Y claro, lógicamente, en función de la rigidez, de la dureza de los granos, de lo mayor o menor resistencia de los granos, pues tenemos un valor u otro, ¿vale? Materiales mucho más rígidos, arenas, cuarzos y demás, o materiales mucho más, digamos, moldeables, con menor resistencia de los granos. O sea, esto ya se sabía que había un tramo inicial recto, pero que si hablábamos de rangos de tensiones muy altos, pues ya se incurvaba. Vamos a hablar de un tema que vamos a usarlo, que es, digamos, el índice I de Bishop, que es, digamos, la pérdida de resistencia que tenemos, a mí se llama I de Brittle, de fragilidad, ¿vale? Y es la formulación que tenéis ahí arriba, en el cual a mayor pérdida de resistencia, esta flecha azul, ¿vale? Tendremos una IB mayor. Es decir, si yo digo que la IB es 0, es que no hay pérdida de resistencia. Si digo que la IB es 60, es que he perdido, no me he quedado con el 60% de resistencia, he perdido el 60% de resistencia, ¿vale? Bueno, pues si analizo con la formulación de Robertson 3 ensayos que hizo Jeffrey Sibin en el 16, tenemos 3 ensayos con distintas presiones, esto es muy importante, cojo los resultados de los ensayos, los paso a la formulación que propone Robertson en el 2017 y veo que en esos 3 ensayos me da pues que la IB para el primero de los ensayos, con una presión más reducida, tenemos una IB, una pérdida de resistencia del 90%, una pérdida de resistencia del caso B del 40% y una pérdida de resistencia del caso C del 20%. Es decir, en principio el 20% hemos dicho que no sería una licuación por flujo, no me daría demasiados problemas, ¿vale? Es decir, ¿dónde estarían los problemas? Los problemas con grandes pérdidas de resistencia, si eso es lo que nos preocupa, los tendríamos cuando estamos en este rango. Cuando la distancia entre la LCC, la línea de estado crítico y la LCC sería mayor, ¿vale? La Limited Compression Curve sería mayor, ¿vale? Si cogemos los datos de la gráfica de Sadrekarim y Olson, que cogieron muchos ensayos de laboratorio y analizaron para arenas limosas y limos arenosos, hicieron y analizaron con esos ensayos la pérdida de resistencia, ¿vale? En función de las presiones. Esto es la curva que sacaba Sadrekarim y Olson. Bueno, pues con la interpretación de los ensayos de la arena de Ersan, tenemos que, bueno, pues la pérdida de resistencia, o sea, cuadra perfectamente con los valores que están publicados, ¿vale? O sea, que parece que todo va dentro de lo que cabe cuadrando, ¿vale? ¿Y qué pasa en la realidad? Las roturas que ha habido, lo que se llaman los casos históricos. Bueno, pues en el 2002, Olson y Sark publicaron un listado de casos donde se había pensado que se había producido licuación por flujo y se analizó, hicieron estudios retroactivos, hacia atrás, retrospectivos, perdón, y Robertson los completó con otros datos y entonces, si cogemos estos ensayos, estos no son ensayos, son datos de roturas históricas y los ponemos en la gráfica de Sadrekarim y Olson, los valores de los casos históricos estarían situados más o menos en esta zona. ¿Qué quiere decir esto? Bueno, pues que la pérdida de resistencia que se ha producido en los casos de rotura por licuación por flujo que han tenido daños es superior a 0.4. Están por aquí. Es decir, se ha perdido el 40%, el 50%, el 60%, el 70% de resistencia. Y la resistencia post-licuación van a ser valores por debajo de 0,15 de la tensión vertical efectiva, ¿vale? Es decir, estaríamos en este rango, ¿vale? Ya hemos visto que cómo podemos caracterizar el suelo, pero yo tengo una obra, yo quiero saber si ese suelo va a ser licuable o solamente va a ser contractivo. ¿Qué se puede hacer? ¿Qué podemos hacer? Bueno, sabemos todos que la ingeniería avanza en empujones en función de lo que acontecimientos que han ido pasando. Bueno, pues tras el acontecimiento de Niigata, pues resulta que hubo un montón de técnicos estudiando e intentando comprender el fenómeno que sería de movilidad cíclica, como hemos visto, ¿vale? Entonces, se hicieron un montón de ensayos de laboratorio intentando reproducir lo que pasaba, ¿vale? Entonces, bueno, simplemente os traigo estas imágenes de distintos ensayos para que veáis cómo los ensayos de laboratorio son muy sensibles a la manipulación de la muestra para obtener resistencias. En este caso no estamos hablando de licuación por flujo, pero son resistencias frente a movilidad cíclica. Pero, por ejemplo, rápidamente, o sea, el número de ciclos que salen para una cierta tau, nosotros influye muchísimo el grado de saturación de la muestra de laboratorio. O sea, si es del 100% estaríamos aquí, pero si es el 99,5%, el número de ciclos no tiene nada que ver. Y si es el 99% de saturación de la muestra, el número de ciclos no tiene nada que ver. Pero tampoco es lo mismo tomar muestras inalteradas que intentar una muestra alterada reproducir el sistema, digamos, de preconsolidación que tenía o la historia tensional. No tiene nada que ver. Y tampoco es lo mismo en el laboratorio ponerlas con una mezcla en húmedo, una mezcla polvoreada. O sea, todo depende. O sea, depende mucho los resultados, que es la imagen que quiero llevaros de los ensayos de laboratorio, de los resultados que vamos a obtener. Entonces, ¿estoy diciendo que los ensayos de laboratorio no valen? No, en general, no es que no digo que no valgan, sino que en general están muy sometidos a lo que es la manipulación del propio laboratorio. Y valen, por supuesto, para establecer modelos generales, vale para establecer comportamientos, teorías de comportamientos, etcétera, etcétera. Pero en general, yo tengo mi obra y quiero analizar vale igual o no, qué riesgo tengo, y estos ensayos, cuanto menos, van a ser, digamos, poco, a lo mejor de una fiabilidad no máxima. ¿Qué hacemos entonces? Pues vamos al campo. Y se nos ocurre, vamos a hacer un ensayo tipo el más habitual, el SPT. Bueno, el SPT sabemos que tiene estos problemas. Sid Idris, para el tema de la movilidad cíclica, planteó la relación entre la resistencia cíclica y la acción sísmica equivalente y en función de los ensayos de SPT o los ensayos de CPT. Bueno, ahí tenemos, no vamos a entrar en ello, los inconvenientes de emplear el SPT. Dependemos mucho del operario, la calidad del operario, la calidad de la limpieza. Con lo cual, en general, yo, como técnico, recomiendo que lo que se tiene que emplear es el ensayo de piezocono. El ensayo de piezocono es un ensayo que está muy adaptado a este tipo de materiales, porque sabéis que es originario de Holanda, que los suelos ahí son muy, muy blandos, son arenosos y muy, muy blandos. Normalmente no tienen ningún tipo de plasticidad, entonces es muy adecuado para este tipo de suelos. No hay que hacer un sondeo, podemos hacerlo rápidamente, es muy repetitivo los resultados, o sea que en principio parece que es un ensayo que se adecua bastante a este tipo de estudio. Bueno, pues si nos centramos rápidamente voy a pasar por la historia de los CPTU, un poco orientado sobre todo a la parte de la ecuación por flujo. Bueno, aquí empezamos, esto viene desde el 81 de Douglas y Olsen. Se tomaban los datos directamente y se analizaban los resultados que se obtenían. Robertson y Campanella establece, bueno, pues vamos a hacer una cosa, vamos a introducir una cierta no normalización, sino variación en los resultados que medimos, la Q sub T, y vamos a analizar y vamos a dar qué tipo de suelo tenemos. Esto ya lo conocemos todos. Más adelante, Robertson plantea ya él solo, plantea que vamos a normalizar tanto lo que es la resistencia por momento de fricción y vamos a normalizar también la resistencia del cono. No vamos a emplear ya unidades de presión, no son valores directos, sino vamos a normalizar en función de la profundidad. En el 90. Y en el 2010 ya será otro salto que es, a ver, se han visto que si se normalizan esos datos con la QTN, que son los valores que tenéis ahí, lo que se observa es que hay un índice, un IC, que nos permite establecer del Seguridad Type, el tipo de suelo, nos permite establecer una graduación continua, ya no vamos saltando en saltos el 2, el 4, el 8, sino tenemos el 2,1, el 2,2, podemos hacer, y cumpliríamos, si se puede ver aquí, digamos, los valores para esos valores, para eso, digamos, esa variable IC, pues prácticamente se pueden considerar como son círculos concéntricos, lo que nos facilita mucho la interpretación, ¿vale? Y ya en el 2016, aquí introduce Robertson, hasta aquí hablaban del comportamiento del suelo, soil behavior type, comportamiento es una arena, es una arcilla, y en el 2016 se orienta mucho más los resultados de los piezoconos, se orienta mucho más ya al comportamiento de licuable o no licuable. Y ya se habla de un CPT drenado, no drenado, un CPT ya no se dice que es arcilla, sino que se dice es un comportamiento tipo arcilla, es un comportamiento tipo transicional, es un comportamiento tipo arena. Vale, y hemos visto que para que el suelo sea licuable tiene que ser contractivo. No todos los contractivos son licuables, pero todos los licuables son contractivos. Bueno, pues se establece la relación, el punto de paso, un valor CD, contractivo o dilatante, se establece esta fórmula y se viene a decir que cuando tenemos CDs igual a 70 es el límite que existe entre lo dilatante, azul, no hay problema, y lo contractivo, habrá posiblemente problemas. Habrá que analizarlo si hay problemas o no, ¿vale? Se establece el valor de C sub D. Y ese establecimiento de lo rojo malo, lo azul, CD 70, el límite, ¿cómo encaja con los datos esos históricos que teníamos. Bueno, pues si se representan los datos históricos que teníamos de esas roturas históricas, pues parece que siempre hay un puntito, que está un poquito fuera, son roturas históricas tipo C, D y E, que son, los datos son menos precisos, porque están sacados ahí los danés digamos, de otras instrumentaciones. A lo mejor no es un piezocono eléctrico, sino son, bueno, pues son registros que se han aproximado a lo que sería el resultado de un piezocono, pero en general parece que encaja bastante bien los resultados históricos con la zona donde se piensa que esos suelos, con un ensayo CPT, podemos decir que puede licuar. Y si incluimos los últimos de Fillao y los últimos de Fillao es del 2019 y el de Fundao del 2015, bueno, pues también encaja bastante bien con este criterio. Es decir, parece que esto es un procedimiento, digamos, aproximado, ¿no? No aproximado, es una aproximación al fenómeno. No podemos ver que, en principio, con un ensayo de piezocono podemos discriminar fácilmente si el material es licuable o no. Bueno, vamos a pasar rápidamente por la resistencia poslicuación, porque, bueno, ya sabemos que va a ser... con el piezocono podemos estimar cuándo el suelo va a ser posiblemente licuable o no. Entonces, en el artículo que os he comentado antes de la revista Geotecnia están toda la evolución hasta obtener esta gráfica del 21. Esta gráfica es original de Peter Robertson, que me la pasó directamente el formato, porque la que tenía yo disponible se veía mal. Es esta gráfica la de resistencia, ¿no? Entonces, se establecen dos tipos de comportamiento. Ahí tenemos para un comportamiento de IC menor que 3 tipo arena y para un comportamiento a presiones menores de 3 atmósferas. Está en el gráfico. Y para un comportamiento para IC mayor que 30, para un comportamiento tipo arcilla. Importante. ¿Y esto encaja esas resistencias con las estimadas en los casos históricos? Pues importante, los casos históricos estarían por encima de la resistencia. Es decir, esto es una envolvente de seguridad. Por encima de estos valores que podemos obtener, estarían las resistencias que se estiman que hubo en esos casos. Es decir, esto es una envolvente de seguridad. ¿De acuerdo? Bueno, pues si juntamos el gráfico de antes para saber si el suelo era licuable o no, esto ya lo habéis visto en la ponencia de Manuel, con las resistencias de estos gráficos, si juntamos cuando el suelo es licuable y no, y con las resistencias, obtenemos estos gráficos que propone Robertson en el 21, que son en función del punto de mi ensayo, aquí lo tenemos, yo en función de dónde me esté mi ensayo piezocono, pues estaré más o menos cerca. Si estoy por arriba, mi piezocono, no voy a tener problemas de licuación. Si estoy por debajo, cuanto más abajo esté, estaré en una curva, en una isolínea de resistencia poslicuación. Hacemos esto con todos nuestros piezoconos en la zona de interés para nosotros y, según Verdugo, nos recomienda, Ramón Verdugo, chileno, ingeniero chileno, nos recomienda, hacemos un histograma de todos los datos que hemos obtenido con la metodología de Robertson, estimamos la probabilidad acumulada y tomamos, por ejemplo, un valor correspondiente al 20% de la resistencia. Y con esto hacemos nuestro diseño. ¿Vale? Insisto, estamos tomando valores del lado de la seguridad. Y estamos tomando el 20%, es decir, todos los valores, el 80% de los casos tenemos valores superiores. Vale, acabo rápido. ¿Y qué pasa a grandes profundidades? Bueno, pues tendremos, cada vez los depósitos son mayores, 50, 70, 100 metros. Los piezoconos no son tan profundos. En general no solemos tener piezoconos tan profundos. 30, 40, 50 metros. Bueno, ¿y qué plantean estos autores? Esto es lo más discutible. ¿Son aplicables estos valores? Dice, bueno, cuanto mayor presión tengamos, estamos más cerca de esta línea nueva, de esa línea de estado crítico más vertical. Con lo cual, estamos fuera del rango donde las pérdidas de resistencia son más importantes. ¿Vale? Entonces, Snide en el 2013 indica que, bueno, los suelos muy flojos y frágiles, cuando están sometidos a muchas presiones, son más dúctiles. Robertson en el 2017, que creo que este artículo está disponible en internet, es muy bueno, y con todos los análisis de ensayo de laboratorio y las indicaciones que hace Robertson, pues considera que estos son los rangos máximos donde podríamos considerar a altas profundidades, a profundidades superiores a 10 atmósferas, la resistencia post-licuación. Esto es, ya digo que es muy discutible, yo lo he discutido con diversos ingenieros, pero bueno, esto es más o menos discutible. Y Robertson recomienda este valor, ¿vale? Y por último, ya hemos analizado la metodología, ya tenemos un suelo, hemos visto, ojo, cuidado, podemos tener roturas, puede licuar, no puede licuar, pero vamos a hacer un depósito, ¿qué nos interesaría? Bueno, pues esta imagen ya la habéis visto antes en la ponencia de Manuel. Bueno, nosotros tenemos vamos a hacer un diseño, bueno, pues con un tipo de material, el ABC, el rojo, amarillo y verde. Bueno, pues para una cierta carga estática, todos los materiales, a no salvo que sean tipo A, no tendremos problema de pérdida de resistencia, pero si tenemos un material tipo C que tiene una pérdida de resistencia, este va a ser el punto C, tendremos un problema de falta de resistencia frente a la licuación. ¿Qué podríamos hacer? Bajar la carga estática, es decir, tumbamos el talud, con lo cual vamos a tener la carga estática más baja. En este caso, la misma resistencia, el material tipo rojo va a tener la misma resistencia y seguimos teniendo problemas porque nosotros vamos a pedir que tenga tensión desviadora, esta de ahí, y vamos a tener la resistencia final esta, ¿vale? Pero ya no tendríamos tanta pérdida de resistencia. Estaríamos con problemas de factor seguridad de la ecuación menor que 1. Y en este caso, ¿qué se recomienda? Bueno, pues vamos a hacer un diseño que vamos a bajar todavía más la carga estática. Y en este caso, un material que sea licuable, no tendríamos problemas de licuación porque la solicitación que tenemos es más pequeña que la resistencia post-licuación. Te robo 2 minutos, Claudio. Conclusiones. ¿Qué es la licuación por flujo? Una pérdida súbita y muy notable. No vale que sea pequeña la pérdida, no tendríamos mayores problemas. Pérdida súbita y muy notable de la resistencia. Son roturas sin previo aviso, auscultación, funciona regular, trayectorias tensionales de muy diversos tipos. Mi planteamiento, que he discutido con el profesor Gens, el profesor Marcos Arroyo. Si puede suceder, sucederá. Si tenemos un material licuable, sucederá. Y ellos me decían, y con toda la razón del mundo, claro, es muy caro decir que todos los depósitos mineros que se analizan y tengan este problema van a licuar, vale. Bien, en esta foto, que es del vídeo anterior que hemos visto, es el caso de Fillao. El problema, la muerte se produjo porque habían puesto los comedores de los trabajadores justamente en el valle. Bueno, yo no digo que se cierren todos pero por lo menos que se sepa que puede pasar y entonces tomar las medidas para qué ocurrirá si pasa, ¿vale? Tomar medidas, diques abajo o lo que sea, ¿vale? Mi idea es, si puede, con tantas trayectorias variables de tensiones, si puede suceder, en algún momento sucederá. Hay un artículo magistral que analiza lo de Brumadinho, que es la rotura de la presa de relaves de Brumadinho en la montaña de cristal del profesor Marcos Arroyo y Antonio Gens. Creo que merece la pena, es una lectura de un artículo brillante. Los ensayos CPTU permiten determinar con razonable fiabilidad la susceptibilidad a la licuación por flujo. Y no solo la susceptibilidad, sino la resistencia post-licuación. Insisto, del lado de la seguridad, ¿vale? Y empleemos modelos robustos de cálculo. Está muy bien emplear modelos muy complicados, modelos con muchos parámetros, pero esos modelos para un usuario, para un manejador de la instalación, a lo mejor se le puede escapar. Para muchas cosas nos valen modelos robustos de cálculo. Simplemente resistencias, SSU, partido de tensión prima vertical, todos los modelos de cálculo lo incluyen, ¿vale? Y por último, si estamos a la hora de hacer el diseño, hagamos diseños poco solicitantes. Bajémonos de ese triángulo azul peligroso a la zona inferior. Y esto era lo último que quería comentaros. Espero que no me haya pasado más que 2 minutos y que os haya sido interesante.
Pues la verdad es que sí que ha sido muy interesante, Javier. Te agradezco mucho tu presentación y luego pues, tenemos oportunidad de discutirlo en el coloquio. El siguiente ponente es Claudio Laya Marañón, que es catedrático emérito de Geotecnia de la Universidad Politécnica de Madrid y que nos va a hablar de las investigaciones geotécnicas del incidente de la presa de Onalcollas. Creo que lo va a hacer también en español, así que Claudio, cuando quieras.
Muchas gracias, Paco, por tu presentación. Supongo que se ve en mi pantalla del ordenador. En caso contrario, hacérmelo saber. Quiero
Sí,
en
se
primer
ve muy
lugar...
bien, Claudio.
Vale,
Sí, se
gracias,
ve
Manuel.
bien.
En primer lugar, quiero agradecer a los organizadores de este webinar la posibilidad que se me ofrece de presentar los estudios que hace ya más de 25 años, se dice pronto, pero son hace más de 25 años, llevamos a cabo en el laboratorio para investigar cuáles eran las causas del mecanismo de rotura de la presa de Andalcollar. Fue un trabajo que se nos solicitó al CEDEX desde la Junta de Andalucía, es decir, desde el organismo público responsable de la gestión de la minería en toda la zona andaluza, y desde el primer momento tuvimos la oportunidad y la fortuna de estar presentes en el estudio de la investigación de las causas de la rotura. Con gran premura de tiempo, en menos de 5 o 6 meses, lo cual es una buena noticia, pero también mala porque impide cerrar algunos de los aspectos que nos hubiese gustado desarrollar con más profundidad. A finales de ese mismo año, en diciembre del 98, como se aprecia en esta fotografía, pues emitimos un informe cuyos documentos constituían un cajón de unos 30 centímetros de ancho que recogían todos los trabajos de reconocimiento de campo, sondeos, geofísica, catas y de ensayos de laboratorio, así como de la interpretación numérica del acontecimiento ocurrido. 3 años después tuvimos la oportunidad de publicar en lo que en aquellos años, estoy hablando del año 98, era probablemente la revista de mayor prestigio en el ámbito de la geotecnia, en Geotechnique. Tuvimos la oportunidad, el director del laboratorio y yo, como responsable del equipo que estuvo trabajando para hacer este estudio, de publicar una síntesis de los aspectos más relevantes, aspectos geotécnicos más relevantes que dieron lugar a la rotura de la presa de Andalcollar. Rotura que tuvo lugar la noche del viernes al sábado del 25 de abril, en el entorno de las 2, las 3 de la mañana. Ya a la mañana siguiente, una avioneta, como se puede apreciar por el vestigio del ala superior de la avioneta, estuvo sobrevolando la zona y tomando fotografías de la zona. En esta diapositiva yo quiero resaltar 3 aspectos. En primer lugar, que solo una pequeña parte de los estériles que estaban almacenados salieron al exterior. En segundo lugar, la proximidad del río Agrio a la ubicación del terraplén. Y en tercer lugar, la presencia en superficie de bloques de arcilla, de margas, de las conocidas como margas azules, términos que voy a utilizar en repetidas ocasiones, que no responden desde el punto de vista profesional estrictamente a lo que son la marga ni el color azul, pero que por utilizarse en términos coloquiales, pues me voy a referir a ellas porque es el verdadero objetivo geotécnico de toda la investigación. Como podemos apreciar, grandes bloques del tamaño de una mesa, de una lavadora, de una nevera, se encontraban presentes en las inmediaciones de lo que fue el gran zanjón, la gran cárcava, la gran trocha, que posibilitó la salida al exterior de una pequeña parte de los estériles que estaban almacenados en la presa, ¿no? En esta diapositiva podemos apreciar también, similar a la que se ha presentado anteriormente, que ya los medios mecánicos de la industria minera estaban en ocupación intentando cerrar y llegando a cerrar rápidamente para evitar nuevos vertidos al exterior. Mi intervención se va a centrar básicamente en ofrecer los datos, es decir, las magnitudes, los conceptos geotécnicos que posibilitan la interpretación de la rotura. Y en primer lugar me voy a centrar en lo que fue la topografía del deslizamiento. Como podemos apreciar por esta diapositiva, es un desplazamiento de grandes dimensiones que afectó a unos 250, 300 metros del terraplén que se comportó como un sólido rígido o cuasi rígido, pivotando en torno a este punto, y que con este brazo de unos 300 metros provocó un deslizamiento entre el alma de las dos superficies, de los dos volúmenes de estériles de la presa, provocó un movimiento en sentido perpendicular a su posición de unos 75-80 metros. Quiero llamar la atención que al fondo está la escombrera. Escombrera que en aquellas fechas tenía del orden de 3 o 4 veces la altura del cuerpo de presa y que inmediatamente fue motivo de preocupación, pero por estar cimentada, alejada de las margas azules, y ya digo el término por segunda ocasión, pues dejó de ser motivo de preocupación en aquellos momentos. Con estos dos datos hay un tercero que es muy significativo, que es el asentamiento que en ese movimiento del terraplén tiene lugar en las partes fundamentalmente extremas del mismo. Esta fotografía fue tomada en persona el mismo día de la rotura, a que acudimos allí varios técnicos del CEDEX, demandados por el Ministerio de Obras Públicas y de Medio Ambiente, responsable y gestor del organismo en el cual estábamos trabajando. Y como se puede apreciar en esta fotografía, hay dos datos muy relevantes. Uno, ese asentamiento que podemos cifrar en la magnitud de una persona, es decir, del orden 1,5 metros, 2 metros. En los artículos y en los trabajos está precisada esta magnitud, pero también el abombamiento, digamos, la deformación con forma de globo que se produce en el cuaternario que está por encima del terciario, en este caso, de las margas azules. Luego, por lo tanto, estos son los datos más relevantes. Sin embargo, cuando nos encontrábamos allí, recorriendo la zona ese mismo día, quizás condicionado por mi experiencia y mis vínculos con la gestión de presas de materiales sueltos y con presas de estériles, pues vimos la presencia de estériles en la coronación de la presa. Y debo manifestar que en mi primera oportunidad o mi primer pensamiento fue pensar, aquí ha habido un overtopping, aquí ha habido un desbordamiento por coronación que ha provocado el deslizamiento. Pero lo cierto es que de manera casi inmediata pudimos llegar a la conclusión que este overtopping sí se produjo, ciertamente tuvo lugar un desbordamiento por la coronación de la presa, pero no fue origen, no fue anterior al deslizamiento general, sino que fue posterior, dado que ese asentamiento provocó que las aguas que protegían a los estériles pudiesen desarrollarse por la coronación de la presa. Y en estas diapositivas nos demuestran esa evidencia de la incidencia de los estériles de la mina, incluso con provocación de pequeñas cárcavas en la dirección del movimiento que había tenido lugar. Pero la evidencia del deslizamiento general por el tipo de movimiento y por el argumento de que había habido un deslizamiento del orden de 1,5 metros, 2 metros, podemos manifestar que el desbordamiento por coronación fue posterior al deslizamiento, fue efecto y no fue causa del mismo. Luego, por lo tanto, los datos clave de toda la investigación, aunque todos los frentes estaban abiertos, es decir, todas las causas que podían haber provocado este enorme deslizamiento desde el punto de vista geotécnico estaban abiertas y eran susceptibles de ser responsables del mismo, tenemos que hay provocado un gran movimiento de una buena parte del terraplén y con presencia de las margas profundas en la superficie. Aspecto que debo manifestar que nada más llegar a Sevilla, los servicios técnicos de la Guardia Civil, es decir, pertenecientes al Ministerio del Interior y responsables del medio ambiente, ya manifestaron, ante nuestra sorpresa, que había sido un deslizamiento profundo afectando a las margas azules. Luego, en definitiva, y a modo de síntesis de este aspecto geométrico, topográfico, debo manifestar que el movimiento se produjo como si un cuerpo rígido se tratase. La escollera se comportó como si un cuerpo rígido fuese, con desplazamientos relativamente importantes, del orden de 300 metros en desarrollo longitudinal y con un desplazamiento del orden de los 75 metros, con un asentamiento importante, cifrable en el 1,5 metros de dimensión, y que fue a través de las margas azules del material que constituye el terciario, dada su presencia en la superficie de la zona. Como podemos apreciar en esta diapositiva, la geología implicada es relativamente simple. Hay un cuaternario que descansa encima de un material que con mayor precisión podemos calificar como arcillas sobreconsolidadas y carbonatadas de color gris o quizás azulado, pero que coloquialmente desde siempre, desde los tiempos del profesor Jiménez Salas y hasta la actualidad, seguimos denominando como margas azules. El cuerpo de presa, diseñado en el proyecto en los primeros años 70, es decir, hace ya casi 50 años, estaba definido de tal forma que empezaba con un dique inicial de escollera, con una pantalla de bentonita cemento que garantizaba la impermeabilidad del conjunto, habida cuenta de que se tenía dispuesto colocar un material arcilloso a modo de núcleo aguas arriba, continuado por esa pantalla de bentonita cemento que se empotraba en las margas, en el elemento impermeable. De esta forma se conseguía un recinto impermeable que impedía el paso de las aguas contaminadas y de los estériles a través del cuaternario constituido por gravas y por arenas relativamente permeables. Descansando en el material que constituye el núcleo, un material de la zona, denominado localmente como rañas, que son unas arcillas con gravas y gravilla, lo cual es importante, como veremos posteriormente, es decir, no era una arcilla limpia, sino es una arcilla con gravas y gravillas. Descansa en un dren, descansaba, según el proyecto, en un dren, para a su vez descansar sobre el material de escollera que se colocaba en función de las necesidades del vaso y como consecuencia de las necesidades demandadas de almacenar estériles de mina. Lo cierto es que a mitad de la producción, a mitad del recrecimiento de la presa, la colocación del dren se suspendió y por lo tanto ese fue uno de los primeros objetivos de nuestro estudio, efectuar análisis granulométrico de las escolleras que constituyen el espaldón, elemento fundamental de la presa en este caso, y granulometría del núcleo para ver si se cumplían y si era necesario la interposición de ese material filtrante y drenante para evitar los problemas de erosión interna. Y las consecuencias de ese análisis pues, nos mostraban que se cumplían básicamente las condiciones filtro entre un material y otro. A su vez, otro objeto de estudio fundamental fue la confirmación y la demostración de que la pantalla de bentonita cemento estaba rota. ¿Y por qué se hacía esta afirmación y se puede seguir manifestando como tal? Pues por varios indicios muy importantes. El primero, por el aumento de los caudales de flujo a través de la misma que dio lugar a la colocación de varios pozos aguas abajo para recoger ese agua contaminada y bombearlo de nuevo al vaso de la presa. En segundo lugar, como vamos a ver en las fotografías a continuación, por la presencia física de estériles del vaso en el aluvial, en zonas aguas abajo de la cimentación de la presa. Y también de manera complementaria por el aumento a lo largo, por la disminución a lo largo de los años, sobre todo en los últimos años, del pH de las aguas, lo cual indicaba que se estaban contaminando por el material del embalse. Estas son unas fotografías del aluvial aguas abajo de la presa, donde nos constatan, por su presencia, la presunción, con notables rasgos de verosimilitud, de que la pantalla de bentonita cemento estaba rota. A su vez, otro aspecto fue identificar si había posibles planos de debilidad, por utilizar un término general, en esas margas, en esas arcillas carbonatadas, semirrígidas, resistentes que constituían el cimiento y a través de las cuales se había producido el deslizamiento. El CEDES contaba en aquellos momentos y en estos también con un equipo geofísico potente y fue un equipo que trabajó al margen de nuestra directa participación y como consecuencia de distintas técnicas, medición de temperaturas en los sondeos, medición de controles de salinidad, de pHs, de resistividad, es decir, de distintos parámetros geofísicos, en su informe final nos informaban de la presencia de anomalías geofísicas, e insisto en el calificativo de anomalías geofísicas, a distintas cotas, a la 20, 25, 27 y 30, e incluso buzando suavemente en dirección sur-sureste. Pero lo cierto es que si bien estas anomalías geofísicas no fueron evidentes, en ninguno de los sondeos, de las decenas de sondeos que se llevaron a efecto y de su levantamiento cuidadoso, pudimos identificarlas. Es decir, desde el punto de vista mecánico, nosotros, y este puede ser un tema de debate, nosotros no percibimos en ninguna de las columnas de los sondeos anomalía alguna. Lo cierto es que en superficie, en las inmediaciones de la cerrada, sí se observan estas anomalías. Pero claro, estas margas sufren los 30-40 grados de verano que tiene Andalucía y sufren las lluvias y las precipitaciones que también se producen en Andalucía todos los años. Luego es un material que ha sufrido un fenómeno de agresión, llamémosle así, meteorológica, que da lugar a que esas discontinuidades estén presentes a distintas cotas, buzando suavemente, como nos había informado el informe geofísico. Luego, por lo tanto, si bien nosotros no detectamos ninguna anomalía mecánica, ningún plano de debilidad que pudiera tener menor resistencia al corte, lo cierto es que esa singularidad geofísica sí que existía en un medio que, como veremos a continuación, es homogéneo en toda su profundidad. También está el dato de las fuertes, de los elevados caudales que se bombeaban desde los 11 pozos que rodeaban el talud, la zona del talud de aguas abajo. En primer lugar, pido disculpas por la calidad de las figuras. Téngase en cuenta que estas están extraídas del informe que emitimos en su momento, es decir, que estas figuras tienen más de 25 años y lo que he hecho ha sido rescatarlas y ponerlas para vuestro conocimiento. Como podemos apreciar, las cantidades de agua que se bombeaban pues eran muy importantes, del orden de varios cientos de metros cúbicos a la hora, en todos los pozos, diferenciadas las distintas zonas, y esta sería la suma total de los caudales filtrados. Pero lo cierto es que de la identificación, de nuevo, de las columnas de los sondeos, no pudimos detectar más allá de los primeros milímetros de la primera superficie en contacto con el aluvial, no pudimos detectar ninguna interferencia entre estas aguas muy agresivas y la capacidad del subsuelo, de las margas. Lo cierto es que la mayor parte, como vimos en las diapositivas anteriores, de estos flujos se estaban produciendo a través del cuaternario, mucho más permeable y mucho más grueso en su composición granulométrica que las margas azules. Lo que sí se pudo detectar del levantamiento de los sondeos, y no sé si lo dije anteriormente, pero lo repito, había 2 equipos de licenciados en geología identificando de manera independiente cada una de las columnas de los sondeos para después confirmar o contrastar o matizar la información que cada uno de ellos levantaba. Y como consecuencia de ello, en esta diapositiva, que tenemos de manera resumida la sección tipo de la presa, vemos que la profundidad del deslizamiento deducida de los sondeos, pues se produjo a profundidades elevadas, más allá de lo que se podría haber estimado en una primera consideración, que sería a través del contacto. Vemos que alcanza profundidades próximas a los 10-15 metros, habida cuenta que la potencia del aluvial es del orden de 3, 4 y como mucho 5 metros. Y a su vez alcanza una gran distancia alejada del pie del talud. Y esto está deducido directamente de los vestigios que en las columnas de los sondeos se detectaban y que nos informaban de cuál era la geometría que se había producido en aquellos. Luego, el objetivo geotécnico fundamental es el estudio de las margas azules. Ese era la verdadera, el paradigma, el elemento básico, habida cuenta de que teníamos constancia de que el deslizamiento se había producido a través de él. A su vez, los que nos hemos dedicado a la geotecnia desde los años 70, pues hemos trabajado relativamente en abundancia en Andalucía y siempre habíamos sufrido estas margas azules, con deslizamientos en taludes inesperados, con empujes sobre muros que debían haber resistido y que no han resistido, y sabíamos de su complejidad y de su carácter frágil. Pero hasta entonces no se había ensayado de manera fehaciente, como vamos a ver, cuál era el comportamiento tensodeformacional de estas arcillas sobreconsolidadas y carbonatados. En primer lugar, vemos desde el punto de vista granulométrico que se trata de un material muy fino, con casi el 100% de partículas que pasan por el tamiz 200. Y en profundidad, la evolución del porcentaje de limos como del porcentaje de arcillas, pues es prácticamente constante. Es decir, es un material homogéneo que tiene un 30%, casi un 100% de pasante por el tamiz 200 y que tiene un 30% de contenido en limos y un 70% de material arcilloso. Su plasticidad es relativamente alta, por no decir alta, es decir, límites líquidos del orden de 60 a 75 e índices de plasticidad entre 30 y 45. Y de nuevo, la evolución con la profundidad del límite líquido o del índice de plasticidad pues es relativamente constante. Y vemos que adopta valores entre 60 y 70 para el límite líquido y entre 30 y 40 para el índice de plasticidad. El contenido en carbonatos, análogamente, su dispersión es algo mayor, pero entre el 15 y el 30% que varía, vemos que su variación con la profundidad pues vuelve a ser de manera gráfica relativamente constante, ¿no? Y de la misma forma podemos afirmarlo respecto a los valores de la densidad seca obtenidos, como de los cientos de contenidos de humedad que se determinaron, habida cuenta de la importancia que concedemos al contenido de humedad en este material terciario, arcilloso y sobreconsolidado. Pero lo más relevante de toda la investigación son los dos conceptos que voy a manejar a continuación. El primero, el comportamiento frágil. Este material sabíamos, los que hemos sufrido su comportamiento en obra, que era un material frágil. Pero yo creo que es por primera vez en España hicimos ensayos en los cuales se detectaba que tiene un comportamiento pico, a partir de una deformación, su resistencia pues es del orden de la mitad. Y esto nos lo informa los ensayos triaxiales, hechos en abundancia, con velocidades de carga muy reducidas, a tensión controlada y a deformación controlada, es decir, un abanico muy amplio de ensayos triaxiales. Pero también en los ensayos de corte. De nuevo vemos que alcanzado un determinado nivel de deformaciones, su resistencia al corte es casi la mitad. Es decir, su comportamiento a largo plazo tiene la mitad de resistencia que puede alcanzar para pequeñas deformaciones. Y por primera vez en España, porque las otras compañías que estaban estudiando este fenómeno tuvieron que enviar las muestras al Instituto Geotécnico Noruego, hicimos ensayos torsionales para conocer de manera objetiva y cuantificable, y esto es un orgullo en mi persona y sobre todo para la institución en la cual participaba yo entonces, obtuvimos ensayos residuales de las margas azules que coloquialmente he utilizado en técnico. Y nos mostraron un valor del orden de 12 grados. Es decir, del orden de la mitad de lo que valores pico podíamos esperar, es decir, un ángulo de rozamiento interno en efectivas del orden de 24 grados. Estos son los datos básicos que complementan lo que he mostrado anteriormente. Y resalto tres aspectos. Por un lado, la permeabilidad, muy baja, muy reducida. Por otro lado, el carácter expansivo de este material. Expansividad que es importante porque desde el punto de vista de permeabilidad homogeniza el conjunto, sella esas posibles singularidades que pudieron estar presentes de planos de debilidad, de fractura, de lisos, etc. Los sella habida cuenta de la expansividad que tiene. Y finalmente, como dato curioso, interesante, pues que tiene una resistencia a compresión simple del orden de 450 kPa. Luego este es el abanico de datos con el número de ensayos efectuado y a su vez con el coeficiente de variación de cada una de esas propiedades. Y estos datos están tomados directamente del artículo del geotécnico. En definitiva, tenemos un material muy homogéneo con la profundidad, muy fino, relativamente alto de plasticidad, carbonatado, con una densidad del orden de 14 kilonewtons metro cúbico y una humedad del 32%, muy impermeable, relativamente rígido como consecuencia de los ensayos con el presiómetro llevados a efecto, relativamente expansivo y con una fragilidad que aquí llamo alta, pero que puedo decir que es más que notable, porque se reduce a la mitad la resistencia que tiene. Pero lo que quizás fue más sorprendente, porque en definitiva no lo esperábamos, incluso en el interior del laboratorio fue motivo de divergencias y de debates, fue los resultados obtenidos con los piezómetros instalados en el cimiento, a 5, a 10 y a 15 metros de profundidad por debajo del techo de las margas. Y las presiones intersticiales registradas, perdón por la diapositiva si no se ve claramente, las presiones intersticiales registradas son muy superiores a las que se pudieran deducir de la red de flujo, consecuencia del flujo que pudiera estar produciéndose en el material cuaternario. ¿Y esto qué nos indica? Pues que las presiones externas, la carga externa, debido al cuerpo de presa de unos 20 y tantos metros de altura y debido al peso del embalse también de otros 20 y tantos metros de altura, pero con un peso específico del orden de 3, pues que esas presiones intersticiales, a pesar de que la presa llevaba en construcción desde mediados de los años 70, pues no se habían disipado. Y eso es todo. Espero que os haya gustado y en el debate podemos profundizar o cuestionar alguna de las afirmaciones que aquí se han llevado a cabo.
Muchas gracias, Claudio. La verdad es que ha sido muy interesante. Yo creo que fui de los primeros que leí el artículo de Geotechnique cuando lo publicasteis y Y siempre me pregunté por qué no se había quitado ese aluvial, ¿no? Pero bueno, eso es otro tema.
Pues te debo
luego,
decir
si
que
queréis,
esa pregunta en el proyecto se estudió a fondo y en profundidad, hasta el punto de que los que redactaron el proyecto fueron a Londres para tratar con especialistas en cemento, en suelo cemento y en viento cemento, su agresividad frente a las aguas. Y llegaron a la conclusión de que la pantalla de viento cemento era la conclusión. Luego estudiaron a fondo esa posibilidad de efectuar un elemento impermeable, pero decidieron esta otra alternativa.
bueno, pues eso. Luego lo hablamos y los temas de durabilidad y todas esas cosas lo hablamos en el coloquio. Bueno, la siguiente ponencia es del fallecido José María Rodríguez Ortiz, que antes hemos aludido, y de don José Limón López, que es el presidente honorario del SPANCOLD y además es ex vicepresidente de ICOLD, con lo cual no te voy a presentar mucho más porque eres una persona bien conocida en el medio. Así que tienes la palabra y nos vas a hablar de la rotura también de la presa de Ancolld.
Sí, realmente va a ser muy interesante esta jornada en cuanto al tema del Ancolld. Entonces, bueno, voy a deciros en primer lugar, bueno, mi presentación va a ser en inglés, me estaba quedando en español, pero, well, in the case of Ancolld drilling dam failure, was presented this presentation that I'm going to have for first time at the workshop on dam incident and accident was Canguiller held in Stockholm in November 2013. This presentation reflects the results of different studies and research carried out. Not all the studies, because some studies like presented by Professor Olaya is included only partially. Our investigation was developed over almost 14 years with a team of experts who analyzed this accident from multiple points of view. I was the leader working together with Professor Rodríguez Ortiz as main advisor and with contribution on a specific aspect made by experts like Professors Oteo and Sagaceta, among others. Also, we consider some works made by public, UPC, and SEDEX and private organizations. The accident occurred in 1998, and the initial studies, plus those necessary to support the different phases of the judicial process, were prolonged until 2012. Then, the process, the judicial process, made it possible to disseminate the cause of breakage and lesson learned. Professor Rodríguez Ortiz and I worked together during those 14 years, and he should be with us today in this webinar. Unfortunately, he passed away last April, so my presentation wants to be a tribute to this excellent engineer whose achievements are numerous and of exceptional quality, having solved important problems related with tunnels and dam, giving innovative solutions. Well, in the case, on this case, there are not too much published information, perhaps due to non-technical reason for the legal process. And first of all, I want to clarify that my presentation is going to be focused only on technical data and the possible hypotheses made by different experts trying to explain the failure. I have to say that this failure has been very complicated to explain. We are going to see in this webinar, because some technical hypotheses have not well analyzed due to a lack of on-site investigation for post-failure. After the failure, the dam was closed and the reservoir was filled with air, making it impossible to continue searching some evidence to support the different hypotheses. This is the contents. This is the context of the presentation, with a description, the failure, short history with main data, forensic point for back analysis, consider hypothesis, contrast with observed data, difference with prevision, proven fact, and lesson learned conclusion. So, following this. Well, this is the plan view just before the failure. Here you see the western side was dug in the hillside, and the rest was closed by the artificial dike with different heights. There was two reservoirs, as you see, separated by an intermediate dike. The bigger reservoir for pyroclastic waste, less contaminated, and the smaller for pyritic waste, more contaminated. And the forecast was to send the excedent of water less contaminated directly to the Agrio River, and the excedent of water more contaminated was conducted to a treatment plant to purify them before to send to the river. Well, this was the forecast, but in fact, when the failure was produced, during several years, the mine mixed the water, and there was no difference between the contamination in one reservoir and the other. And this was the reason why they decided to build a new treatment plant to purify the water before to send to the river, because there was a serious problem of contamination. The crest level was of this dike was variable depending on the deposition of main material, and the zone in which in the dam was completely destroyed correspond to maximum height 27 meters, located in the southeast of the bigger reservoir. Just we have seen before, just close to the intermediate dike. The Agrio River, you see here the Agrio River, flowed near the dam of the smaller reservoir, giving potential problem of erosion of the dam toe. This was the zone where the dam slide. And siguiente, the cross section as built. You see that the filter ended before the crest level. This was in this cross section. You can see the starter dam with 5-meter height, and the bentonite wall entering the alluvium. After this initial dam, the rock fill was constructed by heightening with mine material, and the impermeability was made with a thick clay wall upstream that you see here. And between the impervious wall and the rock fill was designed a filter. For unknown reason, lack of materials, the filter ended to a level lower than the crest. Siguiente. Well, this is the view from the satellite before failure, and you can see the following aspect. Both reservoirs were completely filled with excedent water, reaching to crest level. Well, this is important because water was a very important point in the failure, as I have to say, because the management of water was not as we can hear this morning to reduce the volume of water. Well, this is not was the case. And here you see that there was a west zone in the embankment in the southeast part of the bigger reservoir. And the river is too close, as you see, to the dam of the smaller reservoir. The main data following, the main data for back analysis is here, the height 22 to 27 meters, storage in reservoir when failure more than 30 million cubic meters. Initial design was made in 1978. Construction of a starter dam was between 1978 to 1980. Construction with mine material from 1980. Dam failure was in April 1998, spilling out more than 10 million of cubic meters of water in sludge, and reaching 42 kilometers downstream to the Doñana National Park. Siguiente. Well, we have seen this picture before. The failure happened, in fact, the night between April 24th and 25th. The following morning this was the aspect of the failure. And here you see was presented also by Professor Olaya that was a bridge of 45 meters in the dam and a bridge in the intermediate dike. And here you can see also the sludge remaining into the reservoir. In the southern dam of a smaller reservoir has disappeared, is not there, and the adjacent part of the dam, bigger reservoir, has a slide. We say always that the dike slide like a door. We have seen also before. Siguiente y siguiente. Bien. This is the shape of the dam after the sliding. And vamos al siguiente. And the forensic starting point for the back analysis was that no eyewitness, doubts on the sequence of failure, confusion on the pore pressure in foundation, discussion on the operative shear strength parameter, poor monitoring of the dam and its foundation, and doubts on the construction history, seepage incident, suppression of filter, etc. So immediately after the failure, there was two hypotheses in the for the sequence of events. First hypothesis, hypothesis A, is that the dam of a smaller reservoir slide. This movement broke the intermediate dam, and simultaneously the adjacent part north to the slide broken for the movement. Yes. And this sequence we see in plan, following siguiente. Before the accident, a slide of the lower dam, an escape of pyritic tailing, breaching of junction, escape of pyritic and pyroclastic tailing. This is the sequence in this hypothesis. And well, field tests confirm, as we think, that fracture foundation was a plane surface, and back analysis tried to find this plane, but all the calculations give circular surface. Siguiente. This is expected failure surface in homogeneous ground. Siguiente. This is with the model. Siguiente. And this is the surface in which try to find the result for this, the explanation of this of the failure. Siguiente. And the back analysis corresponding to this hypothesis was published in 2006, taking into account only the geotechnical aspect and focusing only on the slide of dam. And as for the reason, there was necessary to put in the model a weak layer with an arbitrarily reduced strength. After those articles, some authors have concluded that this was in 2006, and in 2010, in a doctoral thesis presented by Francisco Zavala, directed by Professor Eduardo Alonso, it's possible to see that after those articles, same authors have concluded that the analysis was not able to simulate the location of the fracture in its actual position, very well defined by field observation. Neither was able to follow the development of progressive failure. To reproduce the failure, had to be introduced a weak layer in the position of the fracture, because otherwise the finite element model analysis predicted also a circular type failure. Siguiente. This is the part that I have read. So the finite element analysis reported in James and Alonso in Geotechnique 2006 was not able to simulate the location of the fracture, and neither was able to follow the development of progressive failure, and it was necessary to put a weak layer, artificially put layer, weak layer. Sí, siguiente. Bien, vamos a ir para atrás, por favor. Atrás. No tanto. Esta. Sí. This is the explanation of the failure with this arbitrarily reduced strength and other life plan. Is a very high deterministic back analysis, and well, we continue to the other hypothesis. Siguiente. Well, this is the hypothesis B. In this hypothesis, first is the dike broken 45 meters north to the intermediate dam. The southern part adjacent to this bridge, having lost the support, slide like a door, like a solid, a rigid solid. And the intermediate dike broke with this movement and the difference of water pressure. And siguiente. And this is the sequence of the hypothesis B. So before the accident, breach in the upper dam and escape of pyroclastic tailing, breach in the dividing dam, and slide of the lower dam and escape of pyritic tailing. Siguiente. In our work, we have as advisor Dr. Penman, who published also an article in Geotechnique, and he said there is some evidence to suggest that the main dam failed north of the dividing dam prior to the bodily movement of the main dam adjacent to and south of the dividing dam on a shear plan deep in the marl. Dr. Penman sees more clear the hypothesis B. And I repeat here the short history for the back analysis, because in the other hypothesis there is a lack of the topic related to weather. And here you can see in red the points related with water. High seepage in the tow from November 1994, grouting in junction zone in 1995, wells drilled in the tow to cut seepage, and seepage water pumped approximately 1,000 cubic meters per hour in February 1998, just 2 months before the failure. But I had to insist that the number of wells drilled in the tow was 11 in 1995, but plus 46 in 1998. Because the seepage was not stopped by the grouting, and they decide to put more drainage system, because the worry was that the authorities wants to stop the contamination of the Agrio River. Siguiente. And here we have the records in the downstream gauging station, and you have the green one. The green one is the simulation of one flood wave that corresponds to hypothesis A. Measure at the Lijo is the black curve, and the simulation with two flood waves is near to the reality. So in this graph, we have in hypothesis A, the wave would have had a single peak, and hypothesis B would give two peaks, and the simulation fit well with the measure. Siguiente. Well, this is very important, because we see here the foundation, the ground in the foundation of the dam. In fact, there was an important layer of blue marl, but in the zone of failure, we had brown marls, less resistant, and very weathered. And you see here also the shape of the bottom of the brown marl, suggesting to have a non-ancient river. And siguiente. Bueno, and here you had the drainage system made during this year, during 1994 to 1998. In red, you have in the figure, in red, you have a drainage channel excavated in the toe of the dam, just in the zone who slide, and in the white point that you see are wells, drainage well, and you see the lower figure. You see that the wells was penetrating in the entering in the blue mark almost 11 meter and plus. And this suggests that the blue marks are not so impervious as we have, as they suppose. And the Agrio River was very contaminated by the seepage, and the reason of this well was to catch the seepage and pump to the reservoir to avoid the contamination of the river. And the problem was the lack of capacity of water treatment. And when the failure was produced, a new treatment plan was almost finished when dam collapsed. And as I have said, the depth of the wells gives idea of poor impermeability of the ground in this zone. In the sequence of failure, taking into account the problem related with the low level of the filter and the important seepage, maybe the following. Siguiente. Well, this is you see the embankment, the sand beach. The sand beach was not there because it was only water till the dike. Filter that was not at the same level that the crest, Agrio River, and so. And siguiente. So, hypothesis B is that water goes to the embankment in the upper zone of the dike, of the dam. Siguiente. With increasing seepage. Siguiente. So, overtopping and destruction and the flooding in the river. So, well, this is one hypothesis different than the other that we have said before, and we feel that the water was not too much considered in the hypothesis A because the analysis in that case was focused in the foundation, but it's necessary to have to be very careful with the water that, as we say, is the cause of the failure in water dam and also we feel that in this case. Siguiente. So we feel that the overlooked factor was the deficit in construction. We have many information about the difference between the design and the construction. Change on the discharge point and the excessive impounded water, because this failure without this excessive impounded water has been very different. Also force the foundation seepage through the drainage well at the toe. Lack of warning displacement. The monitoring of the dam was very reduced. A score by the river at the failed dam. For probable existence of fall slide in the foundation. Acid attack to the marly ground, 2 flood waves, and dam mismanagement. We feel that in this case, there was a lack of people with experience in the management of the dam, because there was people who don't have enough knowledge to manage the dam. And the lesson learned, siguiente, the lesson learned well, the proven fact is that they had an important seepage in the breaking zone from 1994. It was needed to grow concrete in 1995. We have documented all this aspect. Pumping wells penetrating up to 11-meter depth in the Blue Marsh in 1997 to avoid contaminating the river. New water treatment plant under construction. Increase of seepage up to 1,000 cubic meters per hour in February 1998. Change in the method of tailing discharge into the reservoir, too much water stored. Without such a big water stored, no environmental disaster, only local damage. And lesson learned is that for back analysis, and that is necessary to perform an immediate and objective analysis of the failure. There was, in this case, there was several teams working on that. Assign a multidisciplinary team and a director. Select the better expert covering all disciplines. I want to insist in this point because it's as we see in other cases, and this moment also, is not only geotechnical aspect who has to be considered. For instance, this morning we talk about less water in the reservoir and to have a spillway. Well, in the case of Ancold, there was any spillway. It's necessary to avoid prejudgment of failure modes. We have to study with all the point of view and identify main and secondary causes, because in this in a failure like this one, there are main cause and also many secondary causes. It is necessary to contrast with observed data and have an operational team with that experience. The importance of training. This is a very important point. And siguiente. So the conclusion from our point of view is that the Ancold dam failure was unexpected and difficult to explain. Some hypotheses elaborated were incomplete and overlooked many factors: seepage, difference in construction and operation, dam mismanagement. No satisfactory back analysis performed, and those published are highly deterministic. A team specialized in operation and safety is essential in the management, and training means safety. And as conclusion also, I have to say that this accident has been a very important starting point for my work as president of SPANCOLD. For instance, during this time after the failure and with my mandate, we edit a manual for PON to help professionals on design, construction, operation and maintenance of ponds. We prepare a completely new technical guide on embankment dams. We prepare a technical guide on operation and maintenance. We promote a new technical guide on the environmental aspect of dam and reservoir. And finally, and very important, we implement during 6 or 7 years a master course on operation of safety and of dams and ponds. I feel that these subjects are essential now in many countries, and this is the reason why from ICOLD, EURCOLD, and SPANCOLD, I propose to extend this course of training on dam safety to a more general level. I propose in several meetings, and I think that we are not going to have this exactly this course, but everybody is worried about this subject as reflects this webinar, and the mentalization is very good to resolve the problem. And one of the problems that we have to say into account, to have into account, that training means safety. So it's necessary to have trained people managing this type of installation. Siguiente. Thank you for your attention.
Pues muchas gracias, Pepe. No puedo estar más de acuerdo con lo que dices de que es necesario tener equipos altamente cualificados para operar estas infraestructuras. Bueno, vamos con un poquito de retraso y nos queda la última presentación, que es las herramientas de auscultación aplicadas a la gestión de la seguridad de presas mineras, que las van a hacer Stefan Hopp y José Cuervo, que son ingenieros civiles y de minas respectivamente, pertenecientes a la empresa OBJETO. Pues empezar cuando queráis.
Okay. Buenos días a todos. ¿Me podéis escuchar y ver la presentación?
Sí, perfectamente.
Muy bien. Bueno, pues I'm going to make the presentation in English. In this today's presentation, my colleague José Cuervo and I are going to continue with where Manuel started this morning. We'll talk about surveillance and monitoring tools applied to the safety management of tailings dams. First of all, I will give a short introduction, and then Jose will present solutions for monitoring sensors, automation systems, and then I will wrap up with software solutions and give a short conclusion. What is the key aspect for an effective monitoring program? So we have to encompass all monitoring tasks, because in the end, monitoring is like a chain where it's only as strong as its weakest part. So that's why we have to consider starting from the design to think about what we really need, take care of the installation. We have very high precise sensors that have to measure in very rough atmosphere. We have to take care about the data acquisition to achieve high quality data, manual and automated data. We have to manage this information, this data, and then have the necessary software in order to analyze the data, not only the software, but also the experts that know how to analyze and evaluate the data, and then the people who can make decisions, and they should receive this information. Regarding the design of a system, there are no off-the-shelf solutions. Every dam is a unique structure, and we have to develop tailor-made solutions and think about the type of structure. What is the construction operation method? We already talked about the downstream, upstream, or centerline construction. Then we have to think about the life cycle that has to be monitored, not only the construction, the operation that is somehow a mixture in the tailing dams, and also the decommissioning phase, which is can take many years. And in line with this, we have to think about if we make automatic or manual data readings, especially in the decommissioning phase when we have less staff available. We should always see how we can get the data and also analyze the data with the required frequency. We should think about the dimensions of the retaining structure or the tailings to see if we need special areas to control, or if we need distributed areas. We have to understand the structure, where are the weak parts with a failure mode identification, and in this way we can identify which variables have to be controlled and where do we have to control them. Sensor type, the precision, the range, if they have to be area control of large areas, and also the protection of the sensor, especially if we have the chemical properties of the water that might attack the sensors. Redundancy of the readings, and also the accessibility of the sensor location during installation, but also for data reading and maintenance. Even if we have wireless sensors, sometimes we have to replace the batteries and the sensors have to be accessible. The most important sensor actually is the human eye. It's used for visual inspection. This should be done periodically, should be planned. The important part is, what do we do with this information? Where do we write down the information if we use paper form or mobile devices? The mobile devices improved. They're all the time better interactive, and in combination with good software, we can synchronize these forms and the information and get directly to the information that is included in the forms. Who should make the visual inspections? Trained team, the operation team, but we also need specialists. Specialists cannot be always on site. So in some cases, they cannot be immediately if you look for immediate solutions, or if we are in a pandemic situation or emergency situation that the experts cannot be on site. So a solution might be to use digital glasses that include a camera, microphone, and a small display. So this allows us to make a teleconference and to have direct contact with experts that are in the office with the technicians who's working on site, and you can still walk around freely and have free hands in order to make notes. Another tool to support visual inspections are drones. Of course, there are solutions, very sophisticated drones that make also scans and which help us to control deformations. But for visual inspections, there are quite easy solutions, cheap, light drones that can be actually piloted by everybody. You don't need special certificates. and which help us to get a different view of the structure and also inspect areas that are not cannot be inspected by foot. Now we'll pass to Jose, who will continue.
Good morning, this is Jose Cuervo speaking. And now we are going to speak about the monitoring tools and monitoring instruments. There is a wide variety of monitoring sensors. However, because the limitation of time in this presentation, we are going to pass only for those that we consider fundamental and the minimum requirements for a monitoring design. When we speak about monitoring, we need to first understand what is identify the control parameters according to the dam design and also the failure models. Also to select the appropriate instrument for each parameter. Distribution of sensors along the dam is also important question. And finally, to choose the most convenient method for measurement. I mean, could be manual or automated. In the left image, we can see a slide, a figure of a scheme of the different instruments to install in a tailing dam. There we will focus now on the piezometers, on the horizontal deformation, mainly with inclinometers or similar, with the surface deformations with topography, radar, or other systems, and finally with the other external variables like sea page, weather, or the reservoir level. Okay. When we come to the piezometer, this is the pore pressure measurement, and this is maybe the most important parameter to understand and to predict what is the behavior of the dam. And it's depending on the installation, depending on the environment, we can use the regular standard with the heavy duty, the vibrating wire mean, also the pushing models, or the acidic for acidic conditions that also could be used. These vibrating wire sensors are compatible with the automatic systems, mainly with, doesn't matter the traditional or the new or the wireless systems, and that doesn't require maintenance once the sensor is installed. When we talk about the distribution of sensors, it's important to cover all the dam. When we see the layout, used to be to define cross section every few meters along the axis of the dam, and obviously we need to know what is the design and the failure mode to put more intense cross sections in the areas, in the weakness areas. Also, when we go to the cross section, it's important to measure different parts of the dam, the main dam, at different heights to define the hydraulic gradient. Also, the core is important to measure, and finally the contact, the interface between the foundation and the dam itself. It's important in monitoring, it's important to put redundancy, to use redundancy in sensors, because in case of failure, you have a problem and probably the cost will be more expensive than the double some sensors. And it's also important when we design the cross section or the section itself to take in mind that they need to be alive during construction. I mean, we need to take care of the different paths of the cables or the grouping itself. When we come to the automation in the piezometers, right now the state of art is in tailing dams is to use the wireless system. This is basically because they cover a large area, allows high frequency readings, is much more than the manual. Easy to installation because we don't have wiring. The system has scalability because in case we need to include more sensors, we can use the same infrastructure. We don't need to do a new one. And there are, in terms of cost, there is a reduction of cost when we compare with the manual, because we don't need so many people to measure, and also we have much more readings and it's more safer. Of course, it has an initial investment, but long term is worth to do automation. Also mention that this is for piezometers, but it can be extended for most of the sensors that we are speaking for tailing dams. When we speak about the internal deformation, the horizontal internal deformation, historically we pass from the manual readings in the kilometer casing to the automatic readings with the in-place kilometers, and the last agent in this sequence is the shape array. Basically, the output of the system is the same. We have horizontal deformation with a good accuracy. Doesn't matter the system, but we need to think about when it comes to a lot of readings, it's worth to do automation because the cost, and also when we speak about the areas with high deformation, the shape array is a better option. About the surface displacement, this is traditional done with the topography, and now we are passing to the satellite and the ground radar. We are going to compare, because there are many techniques. We are going to compare the different techniques with the measurement area, the point density, that is the number of points that we are able to measure, the frequency of reading, that is also important in terms of availability of readings and also cost, accuracy, of course, and the initial and operation cost. This is the table that is summarizing all the methods. When we focus on the topography, of course, the traditional methods is the most used and is still valid. Could be with leveling or with the total stations, and basically we need monuments along the crest of the slide of the dam, and measure it manually. This cost, in terms of cost, is expensive because we have a large operation cost, and in frequency is relatively low. In case we have sensitive areas that we need to have more frequent readings, it's also possible to use the automatic total station that provide high frequency, high precision, but is limited to the area because the distance it need light on size, and also need monuments to put the fixed presence in the dam. It's an automatic system, but it doesn't mean that it's unattended, because it requires the maintenance of the systems itself, and also the office work to check the readings, and as usual. And finally is the GPS, the real-time cinematic, that is more a complement than the monitoring system itself, because the cost is very high and the quantity of points is very low. We need one receiver per each point. For this is considered as a complement more than a monitoring system itself. An alternative to the automatic total station is the ground radar. The ground radar, that the installation is similar. We need a place to install the sensor, and the pro is that it doesn't require monuments of presence in the surface. It's able to measure the surface itself and with a high points density. The cons is also the high initial cost investment that it has, and also the limited output that we have, because we don't have three coordinates deformation. We have only the line of sight. We can redact and calculate others, but the direct measurement is the line of sight of the radar. And finally, we see for the ground deformation, the satellite, the INSAR techniques, that I think now must be in the monitoring of tailing dams, because it's covering large areas, is giving good accuracy, and also is able to measure settlement and also in different components, but it's depending the geometry. And the cons is that they doesn't have the frequency required for monitoring. I mean, it's from weeks to months to monthly reading. So it's a good tool to complement the traditional or the manual surveying, but it's not enough to work along as monitoring system, as a surveying system. When we go to the other parameters that we need to control, is the one of that is very important is the seepage, to control the seepage flow in the dam. This is something that they need to be after when the dam is in operation, because is when we see where the seepage is produced, and we need to manufacture custom boxes to measure the flow in the point. This system is also able to automate with the wireless system, as we saw with the inclinometers or the piezometers, and it's also required maintenance, but it's not too high. And finally, we have the external parameters, that is the hydrostatic, the reservoir level, that we can also measure with the regular systems and add to the automatic system, and the weather conditions, especially temperature, rains, and also when the dam is in operation, like is the tailing dams. We need to know what is the level of the dam and all the tailing levels and everything. We need this input to analyze together with all the others monitoring parameters. So now we finish, and Stefan can continue.
Okay. Regarding the software solutions, actually the software should help us to improve the whole process. So that's why actually the software should cover all or nearly all processes of our monitoring program. Mainly, it is used for the acquisition with mobile devices, with a centralized database, but also we should include information from the previous phases. It's important to register the information from the installation. If there were special occurrences during the installation, what is the installation height, or the calibration numbers that have to be included. Another important aspect is that it's a collaborative software platform in order to improve the communication between all experts, like the surveyor, the monitoring experts, the operation staff, safety engineers, maybe also with the responsible authority. So there are many people that have to feed the database, include new information, and others that have to have this information available, immediately available, and make decisions. And in this way, we bring the dam site where we get the data and the office where we make the decisions closer together in order to improve the safety of our tailing dam. The softwares, there are a lot of solutions. The idea is to turn data into useful information and increase our knowledge about the behavior of our structure. We should combine information from manual automatic readings, from topography, from scans, if possible, also from the visual inspections. There are a lot of types of charts and dashboards that help us to summarize the information, but we should not get blind and don't think that just on one chart or one dashboard we get the information. Is it safe or is it not safe? It always is important to have the evaluation from the experts, and there you need a lot of charts and detailed information that helps us to really understand what is going on. And maybe just to show a general architecture, we have a centralized database where we receive automatic data, which can be received from different data loggers or PLCs. Then we receive manual data, which can be monitoring data or also visual inspections. Other formats from inclinometers, topographies, spatial data from INSA, laser scanners or radar systems. But sometimes we even have to connect our database with other databases where sometimes we have meteorological information or other data from the operation from our tailings. And maybe also make an incorporation with a cooperative network. Maybe just a few ideas about how we can handle visual inspection forms. The idea is not just to have a breakdown of our forms, but also the information that is included in our forms in order to find directly the information if it's related to certain areas or if we have incidents that are still in progress or not. And this, in some software, is also possible to synchronize with BIM models. And in this way, we can easily identify locations of certain anomalies. So this helps even some experts or decision makers that don't know all the details of the dam to easier find the information that is needed. As a conclusion, the monitoring system should be adapted to site-specific requirements. There are no off-the-shelf solutions, and the guidelines and requirements are not enough in order to tell us what we really need. We should encompass all monitoring tasks to make the evaluation efficiently, should include the visual inspections, and the new technologies like drones, INSA, provide additional information to the conventional sensors, but they should not be substituted. The redundancy is also very important. And the software platforms help us to optimize working processes and manage the data efficiently. And in this way, we can make the surveillance useful and precise. Okay, thank you very much.
Muchas gracias, Estefan. Muy interesante. Introduciendo pues, técnicas más o menos novedosas de monitoreo, como el tema de la interferometría satelital, los drones y las plataformas de software para manejar todos estos datos. Bueno, la verdad es que Manuel, pues nos hemos pasado un poquito de la hora, culpa fundamentalmente de la parte ibérica y no de la australiana, que han sido más puntuales. Y bueno, pues cuando quieras, pues modera también conmigo el tema del coloquio. Y bueno, he visto varias manos levantadas y sobre todo pues he visto la de Eduardo Alonso Pérez de Ágreda, que desde luego pues por su trayectoria pues es una persona que sí que si tiene alguna inquietud pues sería bueno escucharle o leerle, no sé cómo se hace. Entonces te doy paso para que tú modeles
Sí, además tenemos algunas preguntas del chat y bueno, no sé de los colegas australianos cuántos. So out of the Australian colleagues, I don't know if Brett and David are still connected. Edgar is connected. Y Alberto, si está, no sé si Eduardo, si le pudiéramos dar paso a Eduardo.
Lo he intentado y no me activa el micro.
Vaya.
Sí.
Ahora.
Sí, ahora te escuchamos, Eduardo. Bien hallado.
Gracias, ¿sí?
Te escuchamos perfectamente.
Bueno, he participado desde el principio, he estado escuchando todas las presentaciones. Me ha encantado verte de nuevo, Manuel, después de un cierto tiempo. tu exhaustiva presentación. Bueno, yo quería hablar un poco de Aznalcóllar, porque es un tema al que le hemos dedicado muchísimo esfuerzo desde el año 1998 y muchos artículos detrás. Y bueno, supongo que no hay tiempo, pero me voy a referir a la presentación de Polimón y simplemente voy a dar 3 o 4 ideas. Lo que él ha llamado la hipótesis A, que era falsa en el sentido de que se colocaba una banda de suelo de baja resistencia a una cierta profundidad para tratar de encontrar lo que se vio en el campo, eso no implicaba en absoluto, ni se decía así en el artículo, que es que pensáramos que eso existía. Algo a priori, pero lo curioso y lo interesante del asunto es que en un material strain softening, es decir, que se reduce la tensión y además mucho con la deformación de corte, y no hace falta mucha deformación de corte, como también se ha explicado, si se construye una presa en dirección hacia aguas abajo de la manera en que se construyó, se demuestra y se demostraba en el primer artículo que publicamos, incluso trabajando únicamente con pura elasticidad, que en efecto el conjunto de puntos que correspondían al mayor intensidad de la relación entre el esfuerzo de corte y la tensión vertical efectiva, es decir, por lo tanto, la fricción, era una línea subhorizontal. Es decir, había desaparecido completamente la idea del deslizamiento circular, que en efecto ocurre cuando tienes un material de resistencia uniforme, pero de resistencia uniforme y no variable con la deformación. Ese es el punto clave, porque en cuanto te cae con la deformación, el asunto cambia totalmente. Bueno, años después, en un modelo más perfeccionado, también publicado en Geotechnique, era el 4º artículo ya en Geotechnique, también se demuestra bien que si simulas ese procedimiento de construcción, realmente fue bastante impresionante, porque la superficie de rotura te aparece de forma natural en el análisis donde estaba. Y eso fue con un modelo no excesivamente complicado, que simplemente era un modelo tipo elastoplástico morculón, pero con strain softening, que era la clave. Bueno, y después, posteriormente, también hemos hecho análisis con otros métodos de cálculo ya más avanzados, tipo Material Point Method, para demostrar que la longitud, el empuje que recibió y lo que caminó, que fueron esos 60, 50, 60 metros, también se puede deducir del análisis. Quiero decir que no había nada falso en aquel modelo tipo A, ni pensábamos de ninguna manera que el material era homogéneo. Estábamos precisamente criticando los métodos de equilibrio límite y diciendo, mira, tienes que hacer una hipótesis por las buenas, que no funciona. Eso es lo que decíamos en el primer artículo. Bueno, en cuanto a que hubo una erosión porque saltó por encima parte del agua del embalse y demás, yo creo que no hay ninguna evidencia de campo. Aquello, la presa, una presa muy rígida, una presa de escollera, se movió como un sólido rígido. Me parece que también lo ha dicho no sé quién. Bueno. De modo que la presa guardó sus dimensiones. Curiosamente, uno de los fallos que se cometieron en la construcción es que la presa inicialmente diseñada tenía unas pendientes de los 2 paramentos, aguas arriba y aguas abajo, por cierto eran iguales, pero como si se iban acercando al río Agrio y ya no tenían sitio para poner su presa, fueron aumentando la pendiente. Y eso fue fatal, porque cuando aumentas la pendiente, el estado de tensiones de corte que induces en el terreno de cimentación aumenta. Y los máximos del cociente tau dividido por sigma prima está pues ahí a 14, 15 metros de profundidad. Es bastante sorprendente, pero eso solamente por la elasticidad y después ciertamente lo reproduces. Bueno, no quiero decir muchas más cosas. Hay un tema que ha salido un par de veces, me parece, y es que también lo pensamos en aquel momento. Hombre, ahí tenemos un agua muy contaminada, tenemos ahí abajo unas margas azules. ¿No habrá sido un problema de que esa contaminación por flujo pues ha cambiado la resistencia de la marga? Que por cierto nosotros ensayamos no solamente las margas azules, sino las marrones. y sobre todo los planos que podían ser planos de corte. Y la existencia fue exactamente igual. Bueno, eso ocurre también en la arcilla de Londres, en otras arcillas muy parecidas a las del Guadalquivir, arcillas de alta plasticidad, marinas, tamaño muy fino, muy poca permeabilidad, etcétera, pero que se pueden, a lo largo de algunas discontinuidades, que por cierto las hay, pero son verticales, aparte de los planos de sedimentación, que tienen esa inclinación pequeña, que es la que da ese 1,5 metros, 2 metros, que comentabais también. Bueno, y bueno, pues lo que quiero decir es que esas presiones de agua que se midieron en piezómetros, si eso lo transformas en alturas piezométricas, simplemente te dan un flujo en dirección vertical y hacia arriba, que tiene todo el sentido porque la gran carga de los estériles, que pesan 3,1 toneladas metro cúbico, y la presa, que pesa menos, pero esa gran carga en un material tan impermeable eleva las presiones intersticiales. De hecho, las presiones intersticiales eran artesianas. Lo que pasa es que no salía agua, simplemente es la medida, porque aquello era muy impermeable, no salía agua. Pero estaban por encima de la presa, pero claramente por encima de la presa. Pero como estaban a diferentes profundidades, puedes mirar cuál es el gradiente. El gradiente es hacia arriba. Es decir, no hubo ninguna posibilidad al agua contaminada para que entrara en la marga. Con independencia de que era muy impermeable, es que además el flujo era hacia arriba. Bueno, solamente quería decir eso, pero hay muchos más detalles súper interesantes en esta rotura. José María Rodríguez Ortiz, con el que tuve alguna comunicación Esto ya es para la historia, y realmente me uno a los deseos y al pésame a la familia, además, porque me lo encontré, además, pues en muy buen de salud poco tiempo antes de su muerte, cosa que me impresionó, ¿no? Pero bueno, realmente fue una gran persona, un gran ingeniero, y hablé con él varias veces de este caso. Él decía que Aznalcóllar fue probablemente la rotura geotécnica más importante que había ocurrido en España de cara al estudio, ¿no? Y estaba completamente de acuerdo con él. Me dio una foto súper interesante tomada desde arriba, que yo no la tenía, de toda la zona que se había movido de los estériles, licuefactada, totalmente licuefactada, llena de estas burbujas típicas, ¿no? de los materiales licuefactados. Y luego él también tenía el carácter que tenía y me dijo, oye, que nosotros yo era el perito judicial, me vas a tener que demostrar por qué se movió la parte sur del dique y no la norte, que dice que es el mismo dique. Es cierto que es el mismo dique en una sección transversal, pero hay una diferencia clave. Y es que hay una diferencia de ángulos en su posición, hay 20 grados de diferencia. Y ese cambio de orientación es clave porque si pones en un estudio tridimensional la orientación de los planos de sedimentación que están, difíciles de ver, pero que están, pues entonces te encuentras con que el empuje necesario para romperlo en el dique que no se rompió, que es el largo, el que está por encima, es significativamente mayor al que tienes a favor directamente de la línea de máxima pendiente de esos planos de sedimentación. Bueno, historias que son largas porque ha habido mucho trabajo detrás. Pero bueno, yo me alegro que esto se vuelva a comentar. Yo creo que es un caso que quizá merezca la pena el revisarlo con cuidado, porque hay muchísimas enseñanzas detrás. Y todavía estamos detrás de hacer un análisis más completo en el sentido de que podamos reproducir la licuefacción. Que por cierto, ya me callo aquí, el término licuefacción por flujo, que me ha gustado la presentación, por supuesto, de que no le conocía además, a mí me llama engaño, porque estrictamente en castellano licuefacción por flujo, cualquiera interpretaría, no sé lo que interpretáis, pero que si hay flujo, se licuefacta, pero no hay flujo por ningún lado. Es un tema puramente mecánico y estático, de alguna manera. Es una aplicación de deformaciones de corte que te generan excesos de presión intersticial, etcétera, ¿no? Todo lo que se ha explicado. Pero no por flujo. Bueno, a mí me gusta más decir estático. Bueno, pues lo que decía es que lo último que a mí me falta por entender de verdad es por qué esa aceleración de la presa de Aznalcóllar, porque eso también lo hemos calculado y demás, pero bueno, fue bastante alta, algo así como 0,15 G o así. se desplazó muy deprisa y recorrió esos 50-60 metros en 15 segundos. Nadie lo vio, eso es puro modelo. Pero bueno, el hecho es que aquello se abrió y dejó un enorme hueco donde se desplomaron los tailings. Y eso hizo que se liquefactara. La pregunta es ¿por qué? Bueno, pues hay que conseguir saberlo y en eso estamos, porque es una forma de carga muy peculiar, que ciertamente habrá mucho corte allí, pero que yo sepa todavía no lo hemos hecho, que no hemos sabido hacerlo todavía, pero estamos en ello. Es decir, esa caída de aquella masa grande, ¿por qué lo liquefactó? ¿No? Me parece muy interesante. Bueno, me callo ya porque es tarde y gracias por escucharme un momento, pero encantado de seguir hablando de este asunto cuando queramos. Bueno.
Muchas gracias. Muchas gracias, Eduardo.
Gracias.
Y Paco, ¿qué tiempo tenemos?
Hay muchas manos levantadas. Pues,
sí.
Pues 15 minutos. Entonces, no sé, organízalo como quieras, pero...
Yo si queréis, pasamos un momento.
Voy a pedir la palabra también de voz. Soy Pepe Polimo. Porque evidentemente Eduardo Alonso...
Pepe, habla...
Sí. ¿Que hable qué?
Sí, que hables.
Ah, vale. Vale, no. Yo he aludido a Eduardo Alonso y me alegro de que lo estuviera oyéndolo porque realmente los trabajos que hicieron Eduardo Alonso y Antonio Ollén son excelentes, igual que el de Claudio Olaya también lo es. Y entonces no, me ha parecido que decía que no había hecho nada falso, evidentemente. O sea, los estudios están muy bien hechos, muy completos y la diferencia está, como he comentado, en las hipótesis. El deslizamiento de la presa es lo más llamativo, pero lo que la hipótesis B que elaboramos Rodríguez Ortiz y yo es que ese giro se da porque se rompe la parte que se rompió, que desapareció, y entonces la presa pierde el apoyo lateral y desliza. O sea, todo esto no invalida en absoluto las hipótesis sobre el deslizamiento. Lo que pasa es que lo que sí ocurre es que el fenómeno inicial, desde nuestro punto de vista, es que se rompe un trozo de presa de 45 metros y eso se rompe por lo que pensamos, por lo que he descrito en mi presentación. Y me alegro de que, además de que esté Eduardo Alonso y Claudio Olaya, por supuesto, y me encantaría que se siguiera estudiando porque se pueden sacar muchas enseñanzas del caso de Angus.
Sí, desde luego. Y el tema de la repercusión, además, en la regulación, ¿no? Y en las directivas. Yo estoy sufriendo un poco por los colegas australianos. Entonces, si os parece bien, había una pregunta específica para David Brett y como es más tarde, quizás podemos alargar unos minutos, pero si está por ahí David Brett, si nos importa, le traslado una pregunta del chat. David, are you still connected? I think you are. Yes, there you are. So there's a question from Kimi Rengifo, and she was asking something about the spillway requirements in tailings dams, and whether the spillway should be able to store the PMF event, and also whether the next update of the ANCOLD guidelines, if that will include more detail onto how to estimate the design rainfall for wet season allowance. And I think she's going maybe into hydrological issues that go beyond the tailings dams, but that was the question. So if your thoughts on spillway requirements to store the PMF event.
Yeah, thank you, Manuel. Well, in Australia, we have a requirement that all dams, doesn't matter what the consequence classification is, at closure, you need to design for the PMF. And so, typically this would mean a spillway of some sort or a drainage system that would cater for the PMF, because we believe that we're trying to have something stay for a very long time, and so it's sensible to design for the maximum possible flood that you might have. And bearing in mind that our hydrology is full of unknowns, really, and with climate change, we really have to be very conservative. But I think, basically we really need to have a PMF design, and even for operations, in most cases, we'll be designing for a PMF as well. And it gets very difficult when people want to try and store a flood event on the dam, and it's just very difficult to decide what the parameters you should think about it are going to be. And personally, I always try and avoid it. We should have a spillway, and it should be a very conservative one.
Okay, and that's a very interesting point, because I think there's quite a big difference between the like the ANCOLD approach to PMF for tailings dams and for water dams as well, and maybe the approach in Europe, including Spain, where it's usually like the 1 in 10,000, and that's good to go. Which it's so that we know there's a lot of uncertainty with hydrology, but that's quite a gap, quite a difference in that approach.
Yeah, well, I'm not a hydrologist, but I understand the PMF. If you want to calculate a 1 in 10,000, we have to really start with a PMF, and then you connect the dots of the short duration or the short period of actual rainfall events, and then the PMF, and you join the dots, and then you can guess what the 1 in 10,000 is. But if you do that, why not stick with the PMF anyway? And especially with a closure of a tailings dam, we just don't know what sort of vegetation and erosion and all sorts of things are going to happen. So we need to be very conservative. And usually it's not that much difference in cost to make the spillway larger. And if it's a proper closure, it's going to be a natural embankment of some, or a natural channel of some sort. So I think it's better to be conservative, really.
Okay, thank you so much, David. I would just make a comment respecto, paso un momento al español. Hemos hecho el comentario del diseño de la avenida, ¿no? Que aquí en Australia se utiliza la PMF, y que en muchos casos cuando haces la correlación suele salir un evento de 1 en 100.000 años, incluso más. Es una diferencia muy grande, ¿no? Con el enfoque europeo, incluido el español, que para presas de materiales sueltos se suele ir a el evento de 1 en 10.000 años, ¿no? O sea, ahí hay una diferencia muy grande. Yo hay un tema, porque tenemos más cuestiones en el chat, pero sobre las directivas y la regulación, ¿no? La normativa. Bueno, en España esto viene del Ministerio de Minas y hay un Real Decreto. Me gustaría comentar que, por ejemplo, aquí donde yo estoy, en Nueva Gales del Sur, las presas, da igual que almacenen agua o relaves, lo que se le exige al titular de la presa es independiente de lo que se esté almacenando. Hay un problema de seguridad pública y el tratamiento es análogo en este caso desde el estado de Nueva Gales del Sur, y se exigen revisiones de seguridad, ese análisis basado en riesgo, el tener un sistema de gestión independientemente. Entonces, bueno, respecto a la normativa que ahora mismo tenemos en España y las recomendaciones técnicas para presas de relaves, yo creo que ahí quizás hay deberes que hacer, ¿no? Y desde luego desde el comité y también incluso de la SEPREN, ¿no? Eduardo ha intervenido. Yo creo que deberíamos probablemente tener alguna recomendación más. I was just mentioning, David and Brad and Edgar, that in Spain really is very different what you're asking for, a tailings facility as opposed to a water dam in terms of dam safety management, safety reviews, and even the technical requirements. There's a big difference. And it's not really the case in some case of New South Wales, where really the requirements have nothing to do with the type of impoundment or the material, whether it's a water dam or tailings. But the dam owner really has to comply with basic dam safety requirements. So I don't know if we could comment on that briefly. So, Paco, en español también, si alguien quiere hacer un comentario al respecto, yo creo que ahí tenemos en fin, un tema que deberíamos abordar.
Yo lo que quisiera es terminar a las 2:10, porque me gustaría que cerrara Carlos Granell, nuestro presidente, cerrará este webinar. Entonces, yo creo que hay muchos temas de los que hemos planteado que se van a quedar en el tintero, de los que has planteado tú, de los temas de la necesidad de tener equipos altamente cualificados in situ, digamos, para vigilar el diseño, la construcción, que es toda la vida de la presa minera, y además incluso hasta después del cierre, ¿no? Y, por supuesto, observar el comportamiento de la infraestructura. Hay otro tema que a mí me preocupa mucho, que hemos abordado hoy y no abordaremos, que es el tema de la durabilidad de materiales. El empleo de materiales geotécnicos, podríamos decir, de los tradicionales, cómo se ven afectados los materiales, digamos, construidos por el hombre, pero también, en cierto modo, tradicionales, como son las pantallas de bentonita cemento, se ha hablado antes, de asfálticas o núcleos asfálticos, que también se utilizan bastante en industria minera, ¿no? Y sobre todo el tema de los geosintéticos, el tema de los geotextiles y geomallas, geosintéticos, en relación con su durabilidad, que no la tenemos muy clara, ¿eh? Entonces, esos temas, los temas de constructivos, de recrecimientos hacia aguas arriba, cómo se comportan con materiales tan problemáticos como los tenemos. En fin, yo creo que todo esto da para establecer, pues, dentro de un año, dentro de 6 meses o cuando queráis, otra webinar de este tipo, pero tratando otros temas adicionales, ¿no? Y no sé si hay alguna pregunta de alguien que tú consideres que es interesante hablar en estos 10 minutos que nos quedan, pues adelante, Manuel.
Bueno, sí, José María Niceto, que comentaba además que se tenía que marchar ahora, indicaba que en una de esas visitas a Arnalcollar las botas, bueno, le terminaron con agujeros por bueno, el ataque posible químico, ¿no?, de los materiales. Él hacía ese comentario y luego, bueno,
Sí, bueno,
Carlos
además
Barbero.
él suele comprar botas caras. José María Niceto es de los que se gastan el dinero. O sea, un abrazo a José María, si nos estás viendo.
Sí, ha comentado que tenía que marcharse, me parece, pero sí. Bueno, luego Carlos Barbero ha un poco planteado el tema de la gestión, ¿no?, de seguridad y durante toda la construcción, durante la vida, la explotación, ¿no? Y bueno, y cómo intentar gestionar, ¿no?, con planes de emergencia, ¿no?, y con ese enfoque informado por riesgo, ¿no?, y basado también en el comportamiento de la estructura, ¿no? que se plantea en el boletín 194 de ICOLD, y que también se plantea más genéricamente, ¿no? en el estándar de, bueno, de la industria minero, ¿no? Del STM. Bueno, y el poder predecir o el poder gestionar estas roturas, ¿no? Y estos comportamientos con pérdida tan dramática, ¿no? De resistencia del material, con grandes deformaciones y que puede ocurrir en muy poco tiempo, ¿no? Y para que el enfoque del boletín de ICOL es bueno, adoptar realmente diseños conservadores desde la fase de planificación, pensando en el cierre, ¿no? En que estas presas de relaves van a estar en explotación durante muchas décadas, pero que luego, bueno, la explotación minera va a cesar, pero la presa y los relaves van a permanecer ahí durante mucho tiempo. Y ahí es donde se exige, bueno, pues que el diseño sea seguro, se exige un seguimiento primero más activo, luego no tan proactivo, y además, bueno, exigencias como ese, por ejemplo, que hemos hablado de la PMF, ¿no? Con recurrencias muy grandes. Edgar tiene levantada la mano. Edgar, por favor, sí, adelante, añade comentario al
Sí,
respecto.
Manuel. Quiero aprovechar la oportunidad que están todos los panelistas involucrados en la investigación de los frailes y las similitudes que tiene con Cadia.
Con
Una
Cadia,
pregunta,
sí, sí, sí.
sí, muy parecido. Una pregunta, Eduardo. Nosotros tuvimos la oportunidad de conocernos en Tasmania cuando viniste en el 2019. Diste una lectura ranking acerca de termodinámica. Y la pregunta que le tengo a todo el equipo que hizo la investigación de los frailes es, ¿consideraron que la presión que estaba leyendo los pisómetros pudiera ser el efecto del shearing, del strain softening que el material estaba sufriendo conforme fallaba? ¿Es eso una consideración posible, válida?
¿Puedo responder? ¿Me oís? Sí.
Sí, te escuchamos, Eduardo.
Claro que puedes.
Bueno, es que claro, piensa que es una arcilla de alta plasticidad y que rompió en una banda muy estrecha, prácticamente sin dimensión vertical. Quiero decir que el piezómetro, los piezómetros esos que había en diferentes posiciones, pues no sé, me parece que no haya ninguno que estuviese centrado en la banda de corte que se fue formando por puro efecto mecánico del strain softening y el avance de la construcción de la presa. De modo que no, que esa presión de agua yo la entiendo como presión de agua realmente estática y generada por lo que he dicho antes, por la carga exterior. Un simple problema de consolidación, vamos, puro terzaje. Encaja bien, además, porque luego en los cálculos que hemos hecho hidromecánicos, digamos que todo lo tienes en cuenta, pues encaja bastante bien. O sea que, bueno, pues no hace falta recurrir a...
Sí, completar, me gustaría decir que teniendo en cuenta la rigidez del material, la impermeabilidad del material, pues los coeficientes de consolidación que tiene ese material, que son muy bajos, los tiempos de consolidación son muy elevados, y esta experiencia no solo ha tenido lugar en Andarcoya, sino también en otras estructuras que se han registrado piezometría en las inmediaciones de estructuras, tipo puentes, y digamos, puentes carreteros y muros. La realidad es que el proceso de disipación es extremadamente lento.
Muchas gracias.
Sí, muy interesante, muchas gracias. Solo un apunte muy rápido, que lo hemos esbozado en alguna de las presentaciones, ¿no? Y son las limitaciones de los piezómetros. Sobre todo si en una misma vertical tenemos solamente un piezómetro de cuerda vibrante y tenemos un flujo eh, muy verticalizado, eh, como es lo que habéis comentado en el caso de Arnald Collar, ¿no? Si tenemos un único piezómetro, la posición real de la superficie freática y cómo está moviéndose el agua en el medio bueno, pues puede tener errores o diferencias importantes con la realidad. Es verdad que hoy en día tenemos la opción de en un mismo sondeo con un solo cable colocar varios piezómetros con un único cable y en la misma vertical, con lo cual esos gradientes verticales sí que se pueden capturar mejor, y cuando hay un flujo con una componente vertical notable, pues los piezómetros de cuerda vibrante, en ese caso, teniendo varios en una misma vertical, ajustan mejor, pero si utilizamos solamente un piezómetro, puede haber diferencias grandes, sobre todo cuando se compara con los perfiles en profundidad, ¿no?
Sí.
Un
Manuel,
CPT.
en Azalcóllar,
Sí.
llegamos a tener inmediatamente después de la rotura, porque se pusieron piezómetros exactamente como dices, 3 en una vertical. Y eso fue ese dato fue definitivo para
Claro,
entender las cosas. Fue definitivo porque nos situó las tensiones efectivas, nos situó el mecanismo y nos permitió desarrollar los modelos, pues porque los teníamos que validar con algo. Exactamente, teníamos esos 3 piezómetros en fila india y en varias posiciones. No muchas, yo hubiese puesto bastantes más, pero bueno, pero ahí es donde vimos claramente cómo iba el agua. Iba muy lentamente fluyendo hacia arriba.
Sí, sí. Es importante tener eso en cuenta porque...
Sí, Manolo, nosotros
Sí.
también colocamos en 3 sondeos 3 piezómetros, es decir, a -5, a -10, a -15, y no sabíamos lo que íbamos a registrar. Si hubiésemos sabido, no hubiésemos colocado 3×3, sino 15×3. Pero en aquellos momentos, sobre todo iniciáticamente, que terminamos en diciembre del 98, la información fue sorprendente y bueno, afortunadamente, se habían hecho 3 sondeos en los cuales se colocaron 3 piezómetros en cada uno de ellos.
Sí, sí. Muy bien, vamos muy justos de tiempo, pero...
Si os
Bueno,
parece, yo
Presas,
creo que ya podemos clausurar que yo quería agradecer a todos los ponentes porque han hecho un esfuerzo, creo que fantástico, y sobre todo pues los australianos que por horarios pues sufren más que los españoles, ¿no? Muchas gracias, creo que ha valido la pena, y sin más cedo la palabra a Carlos Granell para que clausure este.
Okay, thank you all. Thank you, Francisco Sánchez Caro, Director of the Technical Committee of Tailings Dams of SPANCOLD. Thank you also, Manuel Gómez de Membrillera, for organizing this webinar and for the work related with ANCOLD, and especially thank you to the Australian National Committee for the collaboration. Let's continue this type of collaboration, y ya en español, nada, agradecer a todos los panelistas. Creo que el nivel ha sido altísimo. Muchas veces el nivel se puede medir por el grado de interés que la sesión genera y el grado de preguntas y comentarios. Creo que en este caso hemos alcanzado un nivel muy elevado. Y me quedo un poco con lo que ha dicho Paco Sánchez Caro, ¿no? Que ojalá pueda ser este el primer webinar o la primera sesión de varias. Creo que hay una cierta falta de actividad en las asociaciones de ingeniería y en el mundo de las presas con respecto de las presas mineras, que las tenemos un poco olvidadas y deberíamos tratar de cubrir ese vacío. Nada más, muchas gracias a todos.
Adiós.
Hasta luego, muchas gracias.
Adiós, un abrazo a todos, hasta la próxima. Adiós.